Hello there, and welcome to Science for Sleep, where curiosity slows down, ideas settle gently, and even the most complex corners of the universe find room to unfold quietly. Tonight, we're going to drift toward a moment so small, so brief, and so unfamiliar that even the most advanced theories of physics struggle to make sense of it. It's called the Planck time, the first measurable instant after the universe began, and it's as close as science can get to the very beginning of everything. Before we ease into that strange territory, though, I'd love to know something simple and familiar. Where are you listening from right now? And what time is it in your corner of the world as you settle into this quiet moment? It's a fitting thing to ask when we're about to talk about time itself, especially a version of time that doesn't behave like the minutes and hours we know. If you find this pace comforting or the ideas soothing, I'd be grateful if you liked the video or subscribed. It helps this calm little space reach others who might need something peaceful to fall asleep to. Now that you're here, and hopefully settled, we can start easing our attention toward a moment in cosmic history that's almost impossible to picture. Not because it's dramatic or loud, but because it's so small and quick that normal ways of thinking simply don't apply. And still, there's something fascinating about trying to imagine it. The Planck time is the earliest point in the universe that science can reasonably talk about. Earlier than that, our equations stop working. They don't just wobble or get a little fuzzy, they break completely. So this moment, the Planck time, is like the first frame of a film where every frame before it has been lost, or maybe never existed in a way we'd recognize. It's the first step in a timeline that would eventually lead to stars, planets, oceans, and you sitting wherever you are, listening to this gentle explanation of a moment that lasted an amount of time so small that normal comparisons don't make any sense. The Planck time is defined as the moment 1043 seconds after the Big Bang. That number is difficult to relate to anything in everyday experience. Even the fastest things you know, like the blink of an eye or the time it takes light to travel across a room, are so enormously larger than this that they might as well be centuries. But instead of trying to imagine it as a short moment, it helps to think of it as a limit. It's the smallest unit of time for which our current understanding of physics can describe anything with confidence. Anything smaller than that isn't just unknown, it's undefined. The laws of nature as we know them don't apply. They don't have any meaning. And in that sense, the Planck time is the first moment when the universe becomes something we can talk about, even if only with theories that rely on assumptions we're constantly refining. Before this moment, or rather before this measurable slice, the universe was in a state that we don't have the tools to understand. The temperatures were beyond anything we can replicate. The density was far beyond what matter can experience in any laboratory. And the energy levels were so extreme that the basic forces of nature, the ones that we think of as distinct today, were tangled together in a way we can't visualize. Gravity, electromagnetism, the strong and weak nuclear forces, all of them were merged into something unified. It wasn't that they were simply different aspects of the same thing in a poetic or symbolic sense. They were literally indistinguishable. Their differences hadn't appeared yet. The Planck time is the moment when those forces began separating, like threads gently pulling apart in slow motion. And if we could look into that moment with clear understanding, we might learn why the universe ended up with the laws it has now. But the strange part is that the Planck time isn't only about what the universe was doing, it's also about what time itself was doing. At this tiny interval, the usual idea of time flowing smoothly or ticking at a steady rate breaks down. It's more accurate to say that time was not yet behaving like the continuous stream we assume it to be. Instead, some physicists think time might have existed in discrete units, tiny steps rather than a smooth line. Others think time wasn't settled enough to be considered a real dimension yet. It's like trying to talk about hours and minutes in a world where clocks haven't been invented, not even in concept. You can try to describe them, but the meaning you're used to doesn't fully exist. So why does the Planck time matter? If it's such a specialized idea, far removed from the scale of human experience, why spend so much time trying to understand it? The answer is that the Planck time is the earliest moment where the universe we live in becomes something we can follow forward. It's the first time we can talk about cause and effect in anything like the form we experience now. Before it, even the idea of cause and effect may not apply. The properties of space and time themselves were in a state of flux, so the idea of one event leading to another isn't meaningful. After the Planck time, however, the universe begins expanding and cooling in a way that we can trace. Not fully or perfectly, but enough to build models, test equations, and compare predictions with measurements. It's strange to think that everything we know about the early universe, including the particles that make up your body and the stars scattered across the sky, depends on what happened in this nearly unreachable fraction of a moment. The Planck time sets the stage for everything that follows. It marks a boundary between what physics can describe and what lies beyond our current understanding. Some scientists believe that a future theory of quantum gravity, a theory that unifies gravity with the other forces, will eventually allow us to describe what happened before the Planck time, or at least give us a way to talk about it. But for now, it remains a horizon. Not a barrier we can see across, but one that sits at the edge of everything we know. It can feel challenging to imagine this because the numbers involved are so extreme. The energy density, the temperature, the curvature of space, all of it is far beyond anything familiar. And yet thinking about it can be calming when approached slowly. There's something soothing about acknowledging limits, about accepting that even the most brilliant scientists have places where knowledge fades into uncertainty. It reminds us that mystery isn't a failure of understanding, it's simply a nudge toward curiosity, the same curiosity that eventually leads to discoveries. The Planck time is one of those mysteries. It's an invitation to wonder about the earliest moment that still has meaning in the language of physics. As we move deeper into this topic, it helps to picture the Planck time not as a specific moment with a clear image, but as the beginning of a transition. A transition from a state where everything was compressed into a density that defies normal understanding to a state where space could expand, particles could form, and the universe could begin cooling into something structured. It wasn't orderly or peaceful in the conventional sense, but it was the start of the conditions that would eventually allow structure to appear. Even though we can't see into the Planck time, evidence of what followed it is all around us. The uniformity of the cosmic microwave background, the distribution of matter across space, and even the stability of the physical laws we rely on, all trace their roots back to that first measurable moment. In this early instant, space itself was expanding rapidly, though not yet in the phase known as inflation. That comes slightly later, but the groundwork for it is laid during the Planck time. Energy was present, but energy didn't behave the way it does now. It didn't have separate forms like kinetic or thermal or rest mass. Instead, it existed in an undifferentiated state, the same way the fundamental forces were merged. It's difficult to describe this without slipping into metaphor, but the important point is that the Planck time represents the first moment when these distinctions begin to appear. The universe wasn't cooling in the usual sense because the temperature wasn't something that could be measured the way we measure temperature now. Temperature requires particles with definable interactions, and those didn't exist yet in any stable form. One of the challenges in approaching this topic is knowing where our understanding genuinely applies. Physicists have developed impressive models of the universe up to a fraction of a second after the Big Bang, but the Planck time sits at the edge of those models. It's a point where quantum mechanics and general relativity collide, and instead of producing answers, they produce contradictions. Quantum mechanics deals with the smaller scales, where uncertainty and probability dominate. General relativity handles the larger scales, where gravity shapes the motion of galaxies and the curvature of space itself. At the Planck time, these two frameworks are both essential and both insufficient. Trying to apply them together results in infinities and undefined terms. It's like trying to solve a puzzle using two sets of rules that don't agree on what the puzzle pieces are supposed to look like. Some researchers think that space-time at this scale may have been fundamentally quantum in nature, meaning that it didn't have a smooth structure. Instead, it might have behaved like something granular or fluctuating. This idea is sometimes explored through what's called quantum foam, a term used to describe the chaotic, constantly shifting structure that spacetime might have at extremely small scales. In this view, the Planck time isn't just the first moment of ordinary time, it's the point where this chaotic structure begins transitioning into the smoother spacetime that we're familiar with. The universe wasn't calm or stable in the ordinary sense, but it was forming the framework that would eventually allow stability. The challenge is that all of this remains theoretical. We don't have direct access to the Planck time. We can't run experiments that reach those energies, and we can't observe the universe at that scale. But we can build equations, test ideas, and compare predictions with what we see in the later universe. That's why thinking about the Planck time feels both humbling and grounding. It's a reminder that even with limited knowledge we can still explore. We can't see the first measurable moment, but we can use careful reasoning to approach it. And in doing so, we can appreciate the structure that grew from it. Stepping further into this early moment means moving toward conditions that don't resemble anything familiar, but approaching it slowly helps keep the ideas clear. Even though the Planck time marks the first measurable instant, the threshold just before it is where the universe is shifting from something that can't be described with ordinary physics into a stage where explanations are at least possible, even if they remain incomplete. This threshold isn't a border with a sharp edge or a doorway that's swung open suddenly. It's better to think of it as a transition where the dominant rules weren't settled. If someone could look at this moment with clarity, they wouldn't see a burst, a flash, or anything recognizable. They would see the absence of structure turning into something that could eventually support structure. There's a subtle difference between those two states, and it's at the center of why this threshold matters. One of the most striking things about this region of cosmic history is that even the simplest concepts we depend on every day didn't work yet. Space, for example, wasn't something that had meaningful distances. The idea of length requires stable relationships between locations, but this early universe didn't provide those. Time wasn't something that flowed, because flow requires order and sequence, and neither of those existed in a reliable way. Matter didn't exist because matter needs particles, fields, and interactions that were still in the process of forming, and energy, despite being present in enormous amounts, didn't behave in any recognizable way. So the threshold we're talking about is really the point where these elements first begin to gain definable meaning. It's helpful to separate this threshold from the moment just after it, even though they're extremely close in duration. The reason is that the threshold represents a state where the properties of the universe aren't simply unknown. They aren't meaningful. Before this point, making statements about temperature, density, or force interactions doesn't work because these concepts rely on relationships that hadn't stabilized. The Planck time marks the moment when those relationships begin to behave consistently enough for the language of physics to apply. But right before it, there's a region where the equations we use now don't describe anything. It's not that they describe something incorrectly, they describe nothing at all. The threshold is the moment when that begins to change. Trying to picture this can feel a little abstract, and for many people that can be confusing rather than calming. But approaching slowly can make it surprisingly easy to follow. Imagine trying to describe the shape of a room while standing in complete darkness. You can't see the walls, you have no sense of distance, you don't know where anything begins or ends. But then, slowly, a faint outline appears. It's not clear or detailed, but enough of a boundary forms that you can say something meaningful about the shape. That faint outline is similar to what the universe develops at the Planck time. The darkness before it isn't empty, but it doesn't provide definable features. The threshold is where the first outline appears. From there, shape becomes possible, followed by structure, followed by the intricate universe we know. In this threshold, the energy density was beyond any scale we know how to work with. The temperature was at a level where the concept itself wasn't useful yet. And the curvature of space was so intense that the usual meaning of curvature doesn't fully apply. Those details often make this early stage sound chaotic, but it wasn't chaotic in the everyday meaning of the word. Chaos suggests motion or unpredictability, but unpredictability requires rules to break, and motion requires consistent time. The threshold wasn't chaotic, it simply lacked the conditions that would allow order or disorder to exist. In that sense, it was quiet, not in terms of sound, but in terms of activity. Nothing was acting in a way that could be described. That's why quiet threshold is a fitting description. It was the point where the universe had not yet begun behaving in ways that science can follow. Physicists often talk about singularities when describing extreme conditions, but the situation here is different. A singularity is a point where certain quantities become infinite in our equations. These infinities usually signal that the current theory being used doesn't apply. The Planck time and the threshold before it represent something beyond the singularity concept. Instead of simply having quantities become infinite, the quantities themselves stop being meaningful. Gravity, for example, depends on curvature and mass. But before the threshold, mass didn't exist, and curvature had no stable definition. Quantum mechanics depends on probabilities and measurements, but probabilities require states, and measurements require interactions that didn't exist yet. So both major theories of physics, the ones that describe small scales and large scales, find no grounding in this region. The threshold is the last point where these theories fail entirely, and the Planck time is the first point where they begin to work, though only partially. It's worth taking a moment to look at why this matters for understanding the universe. The rules that emerge at this early threshold eventually become the rules that govern everything. The masses of particles, the strengths of the forces, the way space expands, the structure of atoms, and even the formation of stars all depend on what happened during this transition. The threshold is where the parameters that define our universe begin to appear. They don't settle immediately. That process takes time, but their starting values and relationships begin forming here. In a sense, it's the point where the universe chooses the rules it's going to follow, not consciously, of course, but in the way physical processes lead to stable outcomes. One of the most interesting questions about this region is whether something existed before it that caused the Big Bang, or whether the Big Bang was the beginning of everything. The difficulty is that before might not have a meaning here. Time requires a framework. If that framework isn't stable, the idea of a sequence doesn't apply. Asking what came before the threshold is like asking what's north of the North Pole. The question assumes a structure that may not exist, and while different theories attempt to describe what could precede this moment, none can be confirmed because nothing observable from earlier than the Planck time can reach us. We can only measure effects that occurred later. The threshold marks the place where such measurements can begin to connect to theoretical models. Anything before it remains outside what current physics can test. Still, exploring these ideas can be relaxing when approached without trying to force a definitive answer. The goal isn't to solve the Big Bang, but to understand how the universe transitioned into something that science can investigate. The quiet threshold is where this happens. The ingredients that appear later, particles, fields, space and time, don't come out of nowhere. They arise gradually through processes that began here. Even though we can't describe those processes precisely, we know they must have produced a consistent universe, because everything that follows shows a remarkable level of stability. One useful way to think about this threshold is to imagine a system that hasn't yet settled into a configuration. For example, when liquid water freezes into ice, the molecules begin in a state where they move freely. As the temperature drops, they eventually reach a point where they begin forming stable patterns. At first, these patterns are brief and inconsistent. Then they become more stable, eventually forming a solid structure. The threshold before the Planck time is like the moment just before the first stable patterns appear. Nothing is fixed yet, but the environment is approaching the conditions needed for stable behaviour. When the Planck time arrives, those stable behaviours begin to form. The analogy isn't perfect because the early universe wasn't cooling into order in the usual sense, but the idea of a system approaching a state where structure becomes possible is helpful. Another aspect that becomes important at this threshold is the emergence of what physicists call symmetry breaking. At extremely high energies, the fundamental forces of nature may have been unified, meaning they acted as one single force. As the universe expanded and the energy density dropped, this unified force began to separate into distinct interactions. But this separation didn't happen instantly. The threshold before the Planck time is where this process starts, though it doesn't complete until later. The unification and separation of forces is one of the central themes in understanding the evolution of the early universe, and this threshold marks the moment when the conditions for breaking that unity first appear. The universe didn't choose the structure of the forces arbitrarily. The values arise from physical processes occurring in this earliest region. The curvature of space is another aspect that changes rapidly during this threshold. When the universe is extremely small and dense, curvature is intense. As space expands, curvature decreases. But during the threshold, the concept of curvature is unstable. Space isn't smooth or continuous. It may behave in a way that resembles a set of fluctuating components. Once the Planck time is reached, those fluctuations begin stabilizing into a smoother geometry. Later on, general relativity describes this geometry with remarkable accuracy. But at the threshold, before the geometry stabilizes, general relativity doesn't apply. The universe is transitioning from a state that defies geometric description into a state where geometry becomes meaningful. Temperature is another property that slowly gains definition here. Temperature requires particles exchanging energy in predictable ways, and none of those conditions existed before the threshold. But once the Planck time is reached, particles begin to form through quantum processes. Energy begins distributing in ways that can be described statistically. Only then does temperature become a meaningful concept. The threshold is where this shift begins. The universe wasn't hot before the Planck time in the way we describe heat now. It becomes hot once the conditions for heat exist, and those conditions start forming here. Energy density also transitions across this stage. Before the threshold, energy exists but doesn't behave according to the rules of fields and particles. Once the Planck time arrives, fields begin forming structures that allow energy to behave in quantifiable ways. This change is crucial because the later behavior of the universe, including inflation and nucleosynthesis, depends on how energy is distributed. The threshold marks the point where the distribution of energy begins following patterns that can be extended into later models. As this threshold passes and the Planck time becomes measurable, the universe enters a stage where things begin happening in a consistent sequence. Events can be described. Properties can be tracked. Interactions begin following rules that persist through time. And from here, the universe starts developing patterns that eventually lead to larger structures. Knowing that this early moment sets the foundation for everything else gives it a sense of importance, but it doesn't require dramatic imagery. It's simply the earliest point where the universe begins acting like something that could one day contain galaxies, stars, planets, and the conditions for life. This slow transition is what allows the universe to settle into the patterns that will continue forming as it expands. The threshold is the point before those patterns appear, and understanding it helps connect the immeasurably small instant after the beginning with the vast structured cosmos that follows. As the conditions of the earliest instant begin settling into something recognizable, the universe enters a stage where temperature finally becomes a usable concept, even though what it describes here is far beyond anything that exists in the modern world. It is during this stage that heat isn't just high in a familiar sense. It's at a level that removes the possibility of most things having definition at all. The energy density is so extreme that anything resembling structure is immediately broken apart. The term temperature applies, but only in a limited way because the state of the universe is still too intense for stable interactions. This is a moment when matter can't form, forces are still adjusting into their separate identities, and the environment is so energetic that even attempting to imagine it using everyday experiences doesn't get close. Still, a steady explanation helps make it understandable without needing dramatic comparisons. When we think of temperature in ordinary life, we think of molecules moving around, exchanging energy, bumping into each other. These collisions define what we experience as warmth or heat. But during this stage of the early universe, there were no molecules. There weren't even atoms. There weren't stable particles of the kind that eventually become protons and neutrons. The universe was hot in a different way, one characterized by the raw energy present in the expanding field of space-time. At these temperatures, which are measured in the realm of 1032 Kelvin, any emerging particle would be torn apart instantly. Even the most fundamental building blocks of matter couldn't survive for long. Interactions happened, but they were fleeting, unstable, and quickly overridden by the energy of the surrounding environment. The heat here wasn't defined by fire or combustion or anything familiar. Instead, it was the temperature associated with fields at extraordinarily high energies. Physicists define temperature statistically, not by the presence of flames or hot surfaces. For a temperature to be meaningful, there must be a distribution of energy across possible states. Once the Planck time has passed, that distribution becomes possible for the first time, but it is still unstable. Particles attempted to form, but the forces that govern their structure were still shifting, so they couldn't last. Everything that emerged from the quantum field immediately dissolved back into energy. In that sense, the universe was both active and empty at the same time. It contained enormous amounts of energy, but that energy couldn't settle into anything identifiable. This state is often referred to as a plasma, but the word doesn't carry its usual meaning here. Plasmas on Earth consist of ions and electrons moving freely. What existed in the early universe was much more extreme. The particles weren't simply separated from each other. They couldn't maintain stable identities at all. They flickered into existence through fluctuations and vanished just as quickly. The environment was too hot for any lasting pattern to take shape. Even the concept of a particle becomes somewhat ambiguous in a region where interactions occur faster than the timescales needed for particles to fully form. Instead, it's more accurate to say that the universe consisted of fields in a state of rapid, continuous activity. These fields carried energy, but not in restful or stable ways. The forces operating in this environment were also different from the ones we experience today. The energy levels were high enough that certain forces behaved as though they were unified. Symmetry breaking, a process that would eventually separate the forces, hadn't fully run its course yet. For example, the strong nuclear force and the electro-weak force might not have been distinct. This blending of forces means that interactions didn't follow the rules we're familiar with. When everything is unified, distinctions between the forces lose meaning. Gravity, which had already begun to assert itself separately by this point, interacted with these high-energy fields in a way that's still not fully understood. The universe wasn't chaotic, but it lacked the steady patterns that would later govern how matter forms and how forces behave. The universe during this stage was expanding, but expansion at this time didn't have the same characteristics it later gained. Expansion wasn't something that could carry particles apart because particles weren't stable. It expanded the fields themselves. As the universe grew, the energy density decreased, but not enough to allow stable structures yet. The rate of expansion during this stage wasn't inflation, that comes later, but the early expansion was still rapid. Expansion lowered the energy density gradually, but not by very much. The environment remained too hot for matter to take shape. It was only after this intense period that the temperature eventually dropped enough for particles to form with some stability. What makes this stage particularly fascinating is that many processes that later shape the universe have roots here, even though their outcomes don't appear until much later. For example, the fluctuations in energy density that would eventually grow into galaxies began as tiny irregularities during this early stage. These irregularities were incredibly small, but because nothing existed to smooth them out completely, they persisted. Over billions of years, as the universe expanded and cooled, these tiny differences grew due to gravity. What was once a slight irregularity eventually became regions dense enough to form stars and galaxies. So even though the universe at this time was too hot for structure, the earliest seeds of structure were already present in the form of minute variations. This stage also demonstrates how important cooling is in the development of the universe. Cooling isn't just a process of losing heat, it's a gateway to complexity. As long as the universe remained this hot, the options for structure were limited. Cooling opens doors. It allows particles to remain stable, lets atoms form, and eventually enables molecules, stars, and planets. During this intense early phase, the temperature was so high that all of those possibilities were still inaccessible. Only when the universe expanded enough for the temperature to drop did those options begin to appear. This moment of extreme heat represents a kind of barrier. The universe had to move past it before any recognizable structure could arise. One of the most important questions researchers consider about this stage is whether any deeper theory could describe the behavior of the universe more fully. Our current theories work well starting just after this stage, but inside this high-temperature environment, quantum mechanics and general relativity still struggle to connect. Quantum field theory describes particles and their interactions, but at these temperatures, the behavior of space-time itself must be taken into account. Gravity becomes strong enough in this early moment that it can't be ignored, but general relativity, which handles gravity, doesn't work well at extremely small scales. The combination of these two major theories produces contradictions when applied to conditions of such high energy. That's why physicists search for a theory of quantum gravity, something that could describe both quantum behavior and gravitational behavior in a unified way. This early stage is one of the main places where such a theory would be essential. Even though we can't directly observe this stage, its effects continue to influence the present universe. The cosmic microwave background, for example, carries imprints of the conditions that existed long after this hot stage, but these later patterns are shaped by earlier processes. The uniformity of the cosmic microwave background reflects the fact that the universe was extremely uniform at the earliest times, with only small fluctuations. These fluctuations, as mentioned earlier, originated during moments like this when the universe was too hot for matter, but not too chaotic for small differences to exist. Observing the cosmic microwave background allows researchers to infer what conditions must have been like much earlier. Even though this early stage cannot be observed directly, its fingerprints extend far into cosmic history. Another detail of this period is the behavior of quantum fluctuations. At extremely high temperatures, quantum fluctuations play a more dominant role in shaping the behavior of the fields present in the universe. These fluctuations represent temporary changes in energy that occur spontaneously. In environments like the early universe, they can have meaningful impacts. They can contribute to the small variations in density that later become large structures. While quantum fluctuations are always present, the extreme conditions in the early universe allowed them to influence the large-scale behavior of the universe in ways that wouldn't happen under normal conditions. This connection between the smallest processes and the largest outcomes is a recurring theme in cosmology, and it begins here. It is often tempting to imagine this early universe as turbulent or unstable, but instability requires competing influences and definable structures to react against each other, and at this time, those weren't fully present. What existed was a state governed by energy levels far beyond anything else in cosmic history. The simplicity of that state doesn't mean it was calm. Instead, it means that the options for behavior were limited. Only once cooling occurs does complexity increase. The universe becomes capable of forming particles, fields take on stable configurations, and the interactions that dominate physics today begin to apply consistently. This intense early stage fills the gap between the threshold where the laws of physics first begin to work and the later stages where matter forms. It may seem short on the cosmic timeline, but it's essential because every later development relies on the universe passing through this high-energy state. Some researchers speculate that this period might hold answers to certain unresolved questions in physics. For example, the relative strengths of the fundamental forces could be determined by the behavior of fields during this time. The masses of elementary particles might also trace their origins to processes that occurred here. These values cannot be changed in the present universe. They're built into the structure of physics itself. Understanding the conditions of this early time could one day explain why these values take the forms they do, rather than being different. Those differences could dramatically alter what types of structures are possible. For example, if certain forces were slightly stronger or weaker, atoms might not form, or stars might not be stable. The universe could turn out to be uninhabitable. The extreme conditions of this early stage are one of the main places where those values likely originate. The universe during this stage also existed in a state where matter and radiation were inseparable. Matter couldn't exist because the temperature was too high and radiation dominated completely. As the universe expanded and cooled, radiation would eventually give way to matter-dominated phases. But during this early moment, radiation had full control of the universe's behavior. Radiation pressure influenced the expansion rate. Interactions involving high-energy photons kept the environment unstable for any forming structure. The photon density was enormous, meaning interactions were constant. This radiation-dominated state is one of the defining characteristics of the early universe, and it begins here while the temperature is still far too high for matter. This moment also shows how the universe's earliest behaviours don't map easily onto everyday intuition. We're used to thinking of heat as something that affects objects or materials, but during this early phase, nothing separate existed to receive or respond to that heat. The heat was the state of the universe itself. It wasn't acting on matter. It was constraining the kinds of interactions that could occur. This distinction helps avoid the mental image of particles moving rapidly as a form of temperature. That image works well for gases or plasmas today, but it can't be applied here. Instead, think of temperature as a description of the average energy within the fields themselves. When the temperature is this high, it reflects the total energy density present in the universe. Interactions are rapid, but the lack of stable structure means that the exact nature of those interactions is constantly shifting. As expansion continues, the temperature will eventually fall enough for the next important phase to begin. The environment will still be hot, dense, and dominated by radiation, but not so extreme that particles are immediately torn apart. Once the temperature drops below a critical threshold, the universe will finally be able to support particles with some stability. Their formation marks the start of a new period, where matter and energy coexist in a more balanced way. But to reach that point, the universe must first pass through this intense stage where heat limits the possibility of complexity. Understanding this moment helps explain why particles appear when they do, not earlier. It shows how the earliest environment sets strict conditions that must be met before matter can exist. Moving deeper into the early stages of the universe means entering a region where some of the most familiar ideas about physical reality stop matching the environment. Up until now, we've been discussing conditions that, while extreme, can still be described using energy, expansion, and temperature, even if the values involved are beyond everyday comprehension. But here, we reach a moment where the foundation beneath those concepts begins to shake. Space and time, usually treated as the steady background scaffolding for everything that exists, didn't yet behave like smooth, continuous frameworks. This part of the universe's earliest history is where the underlying structure of reality begins shifting from something unrecognizable to something that can eventually support the laws of physics we live with today. When people think of space, they often imagine a vast emptiness that stretches out in all directions, even if that emptiness contains nothing. Space feels like a blank sheet that can be drawn on. Time feels like a steady current that flows at the same speed regardless of what happens. But neither of those descriptions applies to this early stage. Space wasn't an empty container. It wasn't smooth. It wasn't stable. It wasn't meaningfully divided into distances that could be measured. Time wasn't something that could be counted in regular steps, because regularity didn't exist yet. What we think of as the geometry of space and the flow of time were still forming, and until they settled into something consistent, the universe didn't behave in ways we can easily describe. The idea that space might not have been smooth is one of the challenges physicists face when describing the early universe. In everyday life, space seems continuous. You can move from one point to another without encountering any breaks or discontinuities. Even in the smallest scales we've observed, space appears seamless. But at extremely tiny distances smaller than the Planck length, which is roughly 10 or 35 meters, some theories suggest that space stops being smooth. Instead, it may behave like something granular. Not granular in the sense of sand or particles, but granular in the sense that distances may have smallest possible units. Below those units, the concept of distance loses meaning. If space behaves this way at extremely small scales, it means that during the earliest moments of the universe, the notion of a smooth geometry wasn't applicable. Instead, space might have been fluctuating, changing shape on timescales so short that even calling them timescales feels inaccurate. These fluctuations wouldn't resemble motion or vibration in the way we think of those words. They would be shifts in the underlying mathematical structure that defines what space is. At larger scales, these fluctuations average out, creating the smooth space we live in today. But in these earliest moments, the averaging hadn't happened yet. The universe was still too small and too energetic for stability to appear. Time faces a similar problem in this environment. Normally, we think of time as a continuous sequence of moments. Even when time feels fast or slow psychologically, its actual ticking is steady. But some theories suggest that time may also have a minimum possible unit, much like distance. Below that unit, the idea of one moment following another loses meaning because the concept of a moment hasn't formed yet. Time could be grainy, in the sense that its smallest components are fixed, and anything smaller than that doesn't exist as a physical interval. This idea isn't proven, but it's a serious possibility explored in quantum gravity research. If both space and time have smallest possible units, then this early universe wasn't just hot and dense. It was operating on a framework that didn't yet support continuous behavior. Even using the words before or after is an approximation, since this period represents a shift from a state where time hasn't stabilized to one where time begins functioning in consistent steps. These steps aren't ticks of a clock in the way we experience them. They're more like the smallest distinguishable transitions in the underlying structure of space-time. If time truly is grainy, then the early universe wasn't experiencing time in a smooth flow. It was adjusting into a structure where continuity eventually emerges. Physicists sometimes refer to this unstable structure as quantum foam. The idea is that at extremely small scales, space and time fluctuate so rapidly that they resemble a constantly shifting environment. At larger scales, these fluctuations average into something smooth, but here, before the universe expands enough to support that averaging, the fluctuations dominate. They define the environment, they shape what kinds of interactions can happen, and they limit what can form. This state is not chaotic in a familiar sense, and it's not structured in a familiar sense either. It's simply the state expected when both quantum mechanics and gravity operate at energies and scales where neither theory alone is sufficient. One challenge in describing this moment is that all of our usual language relies on concepts that only exist once space-time has settled. Words like location, duration, distance, and even field depend on stability. But during this early period, stability hadn't formed yet. Locations couldn't be clearly defined because distances didn't behave predictably. Durations didn't exist in the ordinary sense because time didn't flow consistently. The universe wasn't in motion because motion requires a background through which something moves. The background was shifting so rapidly that nothing could form stable paths or trajectories. A useful way to think about this is to imagine trying to draw a line on a sheet of paper that changes shape faster than you can make a mark. The line never stabilizes because the underlying surface doesn't hold still long enough to support it. In the early universe, particles faced a similar problem. They couldn't form sustained identities because the environment didn't stay consistent long enough for them to settle into stable states. The rules that govern how particles form weren't fully established. It took expansion and cooling before the underlying fabric of spacetime became smooth enough for particles to develop lasting structures. Even though this part of the universe is difficult to describe, it plays a crucial role in establishing the conditions that follow. The reason is that once spacetime begins stabilizing, the fluctuations present during this earlier state leave subtle imprints. These imprints aren't visible directly, but they influence later developments. For example, the seeds of cosmic structure, the tiny variations that later grow into galaxies, have their origins in this stage. These variations can be traced back to fluctuations that occurred when space and time were still adjusting into stable forms. Because the universe expanded so rapidly after this stage, these early differences became stretched across vast distances, eventually becoming the starting points for large-scale structures. Another important aspect to consider is the role gravity plays in this early environment. Gravity is usually described as the curvature of space-time, but when space-time itself hasn't formed into a stable geometry, gravity becomes difficult to define. It doesn't behave like the familiar force that pulls objects together or shapes the orbits of planets. Instead, gravity interacts with the fluctuating space-time in a way that isn't fully understood. This is one of the reasons researchers seek a unified theory that combines quantum mechanics with gravity. In this early period, both sets of rules must apply, yet neither set works alone. Only a unified approach could fully describe how space-time behaves under these conditions. Some theories propose that space-time at these scales might not be fundamental at all. Instead, it could be something that emerges from deeper relationships. According to these ideas, the universe at this early moment wasn't built from space and time. It was built from something more basic, and space and time only appear once the system reaches a certain level of complexity. If that's correct, then what we're describing here isn't a distorted version of space and time. It's a pre-geometric state where the fundamental building blocks of reality haven't yet combined into the form we normally recognize. In such a picture, the fluctuation of the early universe is the interaction of deeper components that eventually give rise to space-time as a collective phenomenon. While these possibilities remain speculative, they offer a way to think about this early state without assuming that space and time must behave as they do now. It gives room for explanations that don't require stretching our existing theories beyond their useful range. Instead of forcing general relativity or quantum mechanics to describe this extreme environment alone, these approaches consider the possibility that both need to be replaced by a deeper theory that can naturally handle such conditions. Another element of this early period involves how energy interacts with space-time. Energy density was extraordinarily high, and normally that would mean extreme curvature. But when space-time isn't smooth, curvature doesn't follow the normal rules. The relationship between energy and geometry becomes uncertain. In later stages, energy density influences how space expands. But here, before expansion becomes predictable, the connection between energy and geometry is still forming. This is another reason the universe couldn't support stable particles. Without stable geometry, interactions couldn't follow consistent patterns. Despite the difficulty in describing this moment, the transition out of it is what matters most for understanding how the universe develops. Once space-time becomes smooth enough, even if still unimaginably hot, it begins supporting the formation of fields in a way that can be described. The universe doesn't suddenly snap into shape, it adjusts gradually. The fluctuations slowly lose dominance. The instability in distances and durations becomes less severe. the smallest units of space and time begin merging into a continuous background. At this point, the rules that govern particles, forces, and energy interactions begin working more consistently. This transition doesn't require the universe to be calm, it simply needs expansion. As the universe grows, the most extreme fluctuations are stretched out, losing their ability to influence small-scale behavior. Larger regions become smooth enough to allow fields to form stable patterns. Time begins flowing in a way that supports cause and effect relationships. Distance becomes something that can be measured, even if the measurements are still far from the scales we use today. And the universe begins operating under conditions where the mathematical descriptions of physics begin to apply. It's important to note that even after space and time become smoother, the universe remains very hot and very dense. But the difference between this earlier moment and what comes next is the presence of stability. Once stability begins, even at extreme temperatures, particles can start to form and survive long enough to interact. Forces can separate into distinct identities. Energy can distribute in predictable ways. The path from this chaotic seeming early stage to a universe capable of forming atoms begins with the stabilization of space-time itself. Reaching this point also means the universe can begin cooling in a meaningful way. Earlier, cooling couldn't be described properly because temperature wasn't a stable concept. Once the geometry of space-time supports well-defined interactions, temperature becomes measurable, and as the temperature drops, the universe transitions step by step toward more complexity. Particles begin forming, radiation begins interacting with matter, forces begin settling into familiar forms, the earliest patterns in space-time begin influencing where matter collects. Understanding this moment, where space loses its smoothness and time loses its steadiness, gives insight into why the universe behaves the way it does today. It shows that the continuous time we experience is not a fundamental property of reality. It's something that emerges only after the universe reaches a certain level of order. The smooth geometry we take for granted is likewise an emergent feature. And the fact that these structures emerge reliably is one of the reasons physics is capable of describing the universe at all. As the early universe continues to develop from a state where space and time barely resemble the forms we know, there comes a point where distances finally begin to have definable meaning. Until now, describing the environment required relying on ideas that were constantly shifting. Space lacked structure, time lacked continuity, nothing behaved in a predictable way. But once space-time begins settling into a more stable geometry, even if still extremely small and extremely energetic, the concept of distance starts becoming relevant. The smallest meaningful distance in this forming environment is what physicists call the Planck length, and understanding what this length represents helps make sense of why the early universe behaved the way it did. Distances in everyday life feel straightforward. You can measure the space between two objects. You can stretch out a tape measure or walk from one point to another. Even on very small scales, such as the spacing between atoms, distance still feels like a smooth quantity. But the Planck length, around 10 to the 35 meters, sits at a scale far below anything that can be reached experimentally. It's not simply small, it's the length where the usual understanding of distance no longer works. Trying to discuss anything smaller than the Planck length leads to contradictions in physics. The equations used to describe gravity begin producing infinities. The rules of quantum mechanics fail to describe interactions accurately. Even the idea of smaller becomes uncertain because meaningful measurement seems impossible below this scale. The Planck length is not defined by matter or energy in the way most scales are. It arises from the combination of three constants: the speed of light, the gravitational constant, and the reduced Planck constant. These constants appear in many equations throughout physics, but when combined in a certain way, they produce this remarkably small unit. This combination suggests that the Planck length isn't simply a measurement of convenience. It's built into the structure of the universe itself, representing a fundamental limit to how small distances can be before the usual concept of measurement breaks down. To understand why the Planck length marks this boundary, it helps to look at the relationship between gravity and quantum mechanics. Quantum mechanics allows very small particles to exist in uncertain states. Particles don't have precise positions and momenta simultaneously. Their locations are described by probability distributions. Gravity, however, treats everything as if it exists at definite positions in space-time. When we try to apply both approaches at extremely small scales, the uncertainty allowed by quantum mechanics causes space-time to fluctuate in ways gravity cannot describe. These fluctuations become so intense that space-time itself becomes unstable. At the Planck length, these instabilities overwhelm the idea of distance. Below it, the geometry of space is so disrupted that the concept of length stops having meaning. In the early universe, when space-time was still settling into shape, these fluctuations dominated. The environment was so energetic that attempts to define distances smaller than the Planck length weren't just difficult, they were impossible, because smaller distances couldn't exist in a meaningful way. This is why the Planck length is often described as the smallest step the cosmos can take. Every change in the structure of space-time, at least as far as current theories suggest, happens in increments no smaller than this length. It doesn't mean the universe is made of tiny cubes or grids the size of the Planck length, but it means that measurements or interactions below that scale cannot be described with current physical laws. This limit plays a crucial role in shaping the early universe. When spacetime is dominated by fluctuations at scales near the Planck length, it cannot support stable structures. The geometry shifts too rapidly for particles to form. The forces we know do not behave consistently, and the energy density causes spacetime to warp in ways that make defined distances impossible. Once the universe expands enough so that typical fluctuations are larger than the Planck length, spacetime becomes more stable, distance becomes meaningful, and the environment begins supporting the formation of fields and particles that behave predictably. Even though we cannot directly observe the Planck length, its presence is inferred from the behavior of physical theories. It represents the point where attempts to measure smaller scales inject so much energy into the region being examined that the measurement itself collapses into a gravitational disturbance. In effect, observing something smaller than the Planck length would require so much energy that the observation would distort spacetime. It would create a situation where the act of measuring destroys the possibility of defining the measurement. This limitation isn't due to lack of technology. It's a fundamental aspect of reality. The early universe existed at a time when distances were on the order of the Planck length, meaning the geometry of spacetime was influenced by these fundamental limitations. The reason space seems smooth now is that the universe expanded enough to average out these fluctuations. But back then, the fluctuations were not averaged. They were the defining feature of the environment. Space-time didn't yet have the smoothness needed to form stable interactions. That smoothness only emerged later, when the expansion had stretched space-time to scales where it behaved consistently. It's useful to compare this idea to temperature in a simple material. At extremely small scales, even in a solid object, individual particles move in chaotic and unpredictable ways. But at larger scales, the collective behavior of countless particles produces stable properties like temperature and elasticity. The Planck length functions somewhat similarly, but at the level of spacetime itself. Below this scale, spacetime behaves too unpredictably to support stable distances. Above it, the collective behavior of many fluctuations smooths out into something stable. This doesn't mean spacetime becomes calm or simple at that point. It just becomes describable. It can be treated as a continuous environment for the purposes of physics. In the developing universe, the transition from a space-time dominated by Planck-scale behavior to a space-time that supports larger structures is essential. Once the universe expands beyond this scale, fields begin operating in more predictable patterns. the forces of nature begin separating in ways that respond to the underlying geometry. And energy starts distributing in ways that allow particles to appear. Without this expansion beyond the Planck length, the universe would remain in an environment too unstable for matter, energy, or forces to behave consistently. One of the interesting questions physicists explore is whether the Planck length is truly the smallest possible distance, or whether it simply marks the boundary where our current theories break down. Some believe that future theories, particularly quantum gravity theories such as loop quantum gravity or certain approaches in string theory, might describe scales below the Planck length. But even in those frameworks, the Planck length remains special. It is still treated as the point where classical ideas about space-time stop being useful. Even if smaller structures can be described, they wouldn't resemble distances in the usual sense. The Planck length also impacts how we think about the density of energy in the early universe. If energy is concentrated into a region smaller than the Planck length, that energy would create distortion so extreme that conventional geometry collapses. This leads to the idea that the earliest universe couldn't have had a well-defined shape. There wasn't a smooth curve of space-time that could be mapped. Instead, there was a fluctuating environment where the geometry was uncertain because the scales involved were near or below the Planck length. Only when expansion pushes these scales upward does geometry begin to stabilize. Scientists often describe the Planck length as the scale at which quantum gravitational effects become important. Gravity at everyday scales is incredibly weak compared to other forces, but at the Planck scale, gravity becomes comparable in strength to the other fundamental interactions. This equal footing suggests that the early universe may have been governed by a unified force that later separated into distinct interactions. If so, the Planck length marks the point where the separation begins to matter. Below that scale, the unified behavior dominates. Above it, the forces begin differentiating, each with its own rules and strengths. This unification and subsequent separation help explain why the forces have the strengths they do today. The strong nuclear force, for instance, is very powerful at small distances. The electromagnetic force weakens with distance but remains long range. Gravity is extremely weak at the particle level, but becomes dominant at astronomical scales. All of these characteristics may originate from processes occurring near the Planck scale. The earliest arrangements of fields and interactions determined how the forces would behave once space-time stabilized. Even though we cannot observe that moment directly, the consequences appear everywhere in the modern universe. The Planck length also raises questions about the nature of measurement itself. When we measure distances or intervals, we rely on a stable background. Light travels across a space, and the time it takes gives us a measurement. But if the geometry fluctuates violently, it disrupts the measurement. Light paths no longer follow predictable routes. A beam of light sent across a region smaller than the Planck length wouldn't behave in a measurable way. Its path would be influenced by space-time fluctuations that are too extreme to describe. Thus, the idea of measuring distances smaller than this limit breaks down not because devices are inadequate, but because nature itself doesn't allow those distances to have clear meaning. Another important detail is that the Planck length contributes to our understanding of black holes. According to general relativity, if mass is compressed into a region smaller than its Schwarzschild radius, it forms a black hole. But when you approach the Planck scale, quantum effects become essential, and the behavior of space-time near such extreme densities becomes uncertain. This leads to the idea that black holes might not collapse into true singularities. Instead, they might collapse to something similar to Planck scale structures. If that is true, then the Planck length isn't just a boundary for early universe physics. It's a boundary for the deepest regions of gravitational collapse. This connection between the smallest scales of space-time and the larger scale structures in the universe highlights a recurring theme in cosmology. Processes at unimaginable scales can influence structures across billions of light years. The Planck length represents the smallest structure the universe can meaningfully describe. Yet the fluctuations occurring at this scale may have shaped the distribution of matter in the universe. that eventually formed galaxies and clusters. The waves of density that originated from Planck scale processes were stretched and amplified by expansion, eventually guiding the formation of large-scale structures. Even though we cannot see or measure this length directly, it remains central to many of the theories that attempt to describe the early universe. The formation of space-time, the behavior of forces, and the appearance of matter all depend on the universe expanding beyond this scale. The Planck length is the bridge between a universe where distances don't make sense and a universe where physics begins to operate in predictable ways. As the universe continues to expand beyond the smallest distances where the very concept of length first becomes meaningful, the next feature that begins to matter is the behavior of space-time itself at these incredibly tiny scales. Even after distances larger than the Planck length become possible, the underlying structure doesn't immediately settle into something stable and smooth. Instead, the earliest recognizable form of space-time is marked by constant fluctuations. These fluctuations are sometimes described with the phrase quantum foam. Although the term might sound imaginative, the idea behind it is grounded in the mathematics of quantum mechanics and gravity. It describes a stage of the universe where space-time isn't yet calm enough to be treated as a continuous background. Moving into this part of cosmic history means trying to understand how the earliest traces of geometry behaved. The word geometry in this context doesn't refer to shapes, angles, or curves in the familiar sense. It refers to the mathematical description of how distances and intervals work. When spacetime is smooth, geometry follows predictable rules. Distances remain stable. Paths taken by particles follow consistent patterns. But during this early stage, geometry changes constantly, because the fluctuations at these scales are strong enough to warp distances, shift intervals, and distort the structure of spacetime faster than most interactions could respond. Quantum foam is the name given to this constantly shifting environment. The foam image is not meant to evoke anything physical. It simply suggests that this state is uneven, active, and full of changes happening too quickly for stable formations to take hold. At scales just above the Planck length, quantum fluctuations remain dominant. These fluctuations represent temporary changes in the energy of fields that arise naturally in quantum mechanics. Even in the vacuum of empty space today, fluctuations continue, though at much lower intensities. In the early universe, however, these fluctuations were so strong that space-time itself was shaped by them. The geometry could shift in ways that disrupted any attempt at forming stable structures. This environment wasn't chaotic in a familiar sense. It didn't consist of particles bouncing around, because particles hadn't yet come into reliable existence. It also wasn't gas-like or fluid-like, because those states require matter and interactions that are far too stable to exist at this point. Instead, the activity of the foam reflects the fact that quantum mechanics allows fields to fluctuate, and when space-time is extremely compressed and energetic, those fluctuations influence the fabric of space-time itself. At this scale, gravity becomes strong enough to react to quantum behavior, creating a situation where both quantum mechanics and gravity operate simultaneously in ways we can't yet fully model. Trying to imagine this environment can be difficult because all familiar comparisons fall short. Everyday experiences don't involve space-time changing shape, and the idea that distances can stretch or shrink unpredictably within unimaginably small intervals is far removed from ordinary intuition. It's more manageable to approach the description gradually. Think of this early universe as a state where fluctuations define the environment. Nothing is still, but nothing is structured either. These fluctuations are not motion in space. They are changes in space-time itself. They are not objects moving. They are changes in the conditions that allow objects to exist. Quantum foam arises because of a feature of quantum mechanics called the uncertainty principle. This principle states that certain properties cannot both be known precisely at the same time. For example, the energy of a region cannot be completely fixed if the time interval over which it is measured becomes extremely small. In the early universe, the time intervals available were so short that the uncertainty in energy became enormous. Large fluctuations in energy led to significant fluctuations in space-time geometry, because gravity responds to energy. As a result, the geometry of the universe at these scales couldn't remain stable. It shifted rapidly, never holding still long enough for a smooth structure to form. Even though the foam-like behaviour of space-time seems extreme, it plays an important role in shaping the universe that follows. Fluctuations in energy density at this early stage created tiny differences throughout the forming space-time. These differences were incredibly small, far smaller than anything that would make sense at human scales, but they provided the earliest seeds for the patterns that would eventually grow into galaxies and clusters of galaxies. As the universe expanded, these small differences were stretched and amplified. Much later, they guided the distribution of matter across billions of light years. The environment dominated by quantum foam didn't last long. As the universe continued to expand, the fluctuations became less extreme because the space-time volume in which they occurred increased. Quantum fluctuations remain present in the universe today, but they are far smaller and occur within a stable geometric background. During the early stage, however, there was no such stable background. Geometry and fluctuation were intertwined. The universe could not yet be described using the smooth curves and predictable structures of general relativity. It also couldn't be described solely with quantum mechanics, because gravity was too strong to ignore. This is why quantum foam is considered one of the key indicators that a unified theory of quantum gravity is necessary to understand the earliest stages of cosmic history. The search for such a theory has led to multiple approaches. One idea is that space-time might consist of discrete units at the smallest possible scales, somewhat like building blocks that create continuity only when viewed across large distances. In such approaches, the foam-like behaviour reflects how these units shift and rearrange before forming stable structures. Another idea is that space-time emerges from deeper mathematical relationships rather than existing as a fundamental entity. In this view, quantum foam reflects the interactions of foundational components that do not resemble space or time until they reach a certain level of organisation. Regardless of the approach, the shared idea is that the foam-like state is a sign that space-time we know is not fundamental. It is something that forms gradually. Quantum foam also influences the understanding of black holes and their earliest phases. Near the centre of a black hole, according to classical general relativity, space-time would become infinitely curved. But quantum considerations suggest that space-time at Planck scale energies cannot be treated as smooth. Instead of collapsing into a singularity, space-time might behave in a foam-like manner. If that is true, the extreme environment inside black holes may resemble, in some ways, the early universe. The foam-like state could prevent true singularities from forming. It could instead create regions where the geometry fluctuates at the smallest possible scale, preventing classical collapse into infinity. Returning to the early universe, it helps to consider how this foam-like state transitions into the smoother space-time that eventually supports stable physics. The key process is expansion. As the universe grows, the relative importance of quantum fluctuations diminishes, distances increase, time intervals between fluctuations become larger. The geometry stretches in ways that smooth out local distortions. Expansion doesn't eliminate fluctuations entirely, but it spreads them across volumes large enough that their effects become minor. Once space-time becomes smooth enough, general relativity begins describing it accurately. At this point, distances and time intervals behave predictably enough for matter to form. This transition doesn't happen instantaneously. The foam-like state gradually gives way to a smoother geometry as the universe reaches sizes well beyond the Planck scale. By the time the universe is expanded enough for particles to form and persist, quantum foam still exists, but no longer shapes the geometry significantly. Instead, it becomes a background effect. The space-time that develops after this stage is stable enough for predictable interactions. Temperature becomes meaningful. Forces begin separating more fully. Particles begin appearing frequently and surviving long enough to interact. Expansion and cooling continue to transform the environment into one where familiar physical processes can take hold. It's worth noting that nothingness in this context doesn't mean empty space. Empty space today, even in the most quiet regions between galaxies, contains quantum fluctuations, fields, and low-level energy. The early universe, before the foam-like behavior settled, contained far more activity, not because matter filled it, but because the structure of space-time itself was too energetic and unstable to resemble empty space. The phrase, surface of nothingness, is sometimes used to describe how the foam marks the beginning of space-time, taking a form recognizable enough for physical laws to apply. Before this stage, there is no emptiness as we understand it. There is only the shifting behavior of space-time attempting to stabilize. Another detail that becomes important when describing this stage is the relationship between energy and geometry. In general relativity, mass and energy determine the curvature of space-time. In quantum mechanics, fluctuations in energy are unavoidable. When these two ideas meet in the earliest universe, the result is an environment where curvature changes rapidly. The foam-like structure isn't a random feature. It is the natural consequence of these principles interacting at extreme scales. Without a unified theory, we can't describe these interactions precisely. But the idea that geometry fluctuates follows logically from the combination of quantum uncertainty and gravitational influence. One of the questions that arise from this is whether space-time might have had different possible geometries before settling into the form we observe. Some theories suggest that multiple geometric configurations could have competed before the universe expanded enough for one to dominate. In these scenarios, the foam-like behavior represents not just fluctuations, but an environment where different geometric possibilities existed temporarily. As expansion proceeded, only configurations that remained stable on larger scales survived. This idea remains speculative, but it shows how the foam-like state can be interpreted within different frameworks. Even without definitive answers, the description of quantum foam reinforces an important understanding. The universe at this stage could not support anything recognizable. There were no particles moving through space because space was not settled enough to support motion. There were no stable intervals of time because the idea of a consistent sequence hadn't formed. There were no paths or distances because the geometry changed too rapidly. Yet the universe was not inactive. It was in the process of forming the very framework needed for all meaningful physical behavior. Quantum foam represents that stage of formation. As expansion continues, these fluctuations gradually become small enough that not every detail influences the developing universe. Only the larger scale differences survive to influence the structure that follows. Tiny variations in energy, stretched by expansion, become the seeds for structure. Meanwhile, smaller fluctuations average out. Space-time becomes smooth enough that general relativity applies, at least on scales larger than the Planck length. Once this happens, particles begin forming frequently enough to create a plasma. Forces begin behaving in predictable ways. Radiation begins distributing energy in stable patterns. The early universe now reaches a stage where two major frameworks of physics, normally kept separate in their own domains, are forced to operate at the same time. Under ordinary conditions, gravity is best described by general relativity, a theory that treats space-time as a smooth structure shaped by energy and mass. At the same time, particles and fields obey quantum mechanics, which defines behavior at extremely small scales. In the modern universe, these two sets of rules rarely collide. Gravity governs large structures like planets and stars. Quantum mechanics governs atoms and subatomic processes. They stay in separate sections of physics, each working well in its own territory. But in the early universe, conditions didn't allow that separation. The energy density was too high, the scales were too small, and the curvature of space-time was too intense for gravity and quantum mechanics to remain isolated from each other. They had to operate simultaneously, even though their mathematical descriptions don't align. This moment is important because understanding it would provide insight into how the universe behaved when it was just beginning to form stable laws. Yet this is also the stage where modern physics reaches its limits. Gravity and quantum rules weren't created to work together. When they overlap in conditions this extreme, each theory reveals weaknesses, and neither one can describe the environment fully. Approaching this stage steadily helps keep the explanation clear. Instead of imagining gravity and quantum mechanics clashing dramatically, it's better to think of them as two languages that describe the universe differently. Each language works smoothly when used alone, but when they're forced to communicate in an environment like the early universe, the translation between them breaks down. The grammar of one conflicts with the grammar of the other. Even worse, the words they rely on don't match. Gravity relies on space-time being smooth. Quantum mechanics relies on uncertainty at small scales. When space-time becomes unstable due to quantum fluctuations, gravity cannot rely on smooth geometry. And when gravitational curvature becomes enormous, quantum descriptions become insufficient. This conflict isn't just a philosophical dilemma, it shows up in the mathematics. When gravity is applied at quantum scales, the equations predict infinities that do not represent anything physical. When quantum rules are applied to space-time curvature, the descriptions lose consistency. Physicists refer to these inconsistencies as non-renormalizability, meaning attempts to correct the equations using standard quantum methods lead to results that do not converge. These difficulties indicate that a deeper theory is needed. In the early universe, these conflicting frameworks tried to operate in an environment where neither could provide accurate predictions alone. The fluctuations of the quantum foam distorted space-time. At the same time, the intense curvature created by the immense energy density influenced the behavior of quantum fields. These influences were not optional. They were unavoidable because everything existed in a region so small and energetic that no clear boundary separated gravitational behavior from quantum behavior. This is why researchers say the early universe must have been governed by quantum gravity, even though the precise nature of quantum gravity is still not understood. Quantum gravity is not a separate theory in the way quantum mechanics or general relativity are. Instead, it represents the goal of finding a framework where the rules of both can be combined consistently. Several approaches attempt to describe such a framework. String theory proposes that fundamental particles are tiny vibrating strings, whose modes of vibration determine their properties. In this view, gravity arises naturally from the behavior of one of these modes, and space-time geometry becomes a consequence of deeper interactions. Another approach, loop quantum gravity, treats space-time as being composed of discrete units. These units form networks that produce smooth geometry at large scales, but maintain granular behavior at extremely small scales. Other theories use different strategies, but all aim at the same goal: finding a structure that describes both gravity and quantum behavior within the same framework. The early universe is often considered the best place to search for clues about this unified framework, because it is the one environment where gravity and quantum rules must act together at full strength. In the modern universe, their overlap occurs only in extreme places such as the cores of black holes, regions we cannot observe directly. But the early universe preserved signatures of its behavior in the distribution of matter and the cosmic microwave background. These signatures do not provide a complete picture, but they suggest that the earliest fluctuations, which later shaped galaxy formation, originated from interactions between quantum processes and the expanding space-time. When looking closely at these early conditions, one finds that the energy densities were high enough that gravity couldn't be treated as a weak force. Usually gravity is the weakest force among the four fundamental interactions. In everyday situations, even friction or electromagnetism overwhelmingly dominate. But at the earliest times, the energy scale was high enough that gravity's strength was comparable to the strengths of the other forces, This equality of strength suggests that all four forces may once have been unified. The idea of a unified force is supported by mathematical models showing that at sufficiently high energies, the distinctions between forces disappear. The early universe was at exactly such energy levels. If all forces were indeed unified at this stage, the environment would have behaved very differently from later periods. The rules that distinguish electromagnetic interactions from nuclear interactions wouldn't have existed. Quantum particles wouldn't have had their familiar properties. Gravity wouldn't have stood apart as a separate influence. Instead, all interactions would be described by a single unified framework. Only when the universe expanded and cooled would this unified behavior separate into the four familiar forces. This separation is called symmetry breaking. Symmetry breaking doesn't refer to anything visual. It simply means the rules stopped being identical for all interactions. Once symmetry broke, the universe began behaving according to the differentiated laws we observe today. Before symmetry breaking, gravity and quantum rules didn't just coexist. They functioned in the same environment, influencing each other directly. This is why attempts to describe the early universe using classical general relativity fail. General relativity assumes space-time is smooth, but at these scales, fluctuations from quantum mechanics disrupt that smoothness. It also assumes that gravity can be calculated using continuous geometry. But when space-time graininess becomes significant, the geometric assumptions break. On the reverse side, quantum mechanics assumes a fixed space-time background. But in the early universe, the background wasn't fixed. It was changing too rapidly for quantum descriptions to hold steady. This conflict leads to one of the major difficulties in modern physics: the inability to simulate or calculate conditions at the earliest times without encountering contradictions. For example, the prediction of a singularity at the start of the Big Bang arises from general relativity. If the universe is run backward in time using general relativity alone, the density increases until it becomes infinite. But infinite values signal that something in the model has stopped applying. Quantum mechanics, which forbids perfect localization and infinite densities, disagrees. The fact that quantum mechanics forbids singularities while general relativity predicts them highlights the need for a more unified theory. The early universe, being small and dense enough to trigger this conflict, should be described by a theory that avoids singularities entirely. Some quantum gravity approaches propose that the universe did not begin with a singularity. Instead, they suggest that the early universe reached a minimum size determined by the Planck scale. At this minimum size, space-time could no longer contract because quantum behavior would prevent it. According to these ideas, the universe might have experienced a bounce, where contraction is followed by expansion. Other models propose that time itself behaves differently near the earliest moments, preventing singularities by altering the way time interacts with space-time geometry. While none of these ideas have been confirmed, they offer alternatives to the classical singularity and illustrate the need for a unified theory. One of the most important aspects of this stage is the role played by fluctuations in shaping later structure. Even though the environment was unstable and the mathematical descriptions uncertain, the universe still carried tiny variations in energy density. These variations were the result of quantum processes occurring inside the rapidly expanding space-time. They were extremely small but significant, because the universe later became large enough for these variations to influence the growth of structure. Regions with slightly more energy density would eventually attract more matter. Regions with slightly less would attract less. Over billions of years, these small differences evolved into the large-scale arrangement of galaxies and cosmic voids. Another detail to consider is that quantum mechanics normally describes interactions using probabilities. When gravity becomes strong enough to influence quantum behavior, probabilities themselves become linked to the curvature of space-time. This relationship is not understood well because the usual tools that assign probabilities to quantum events depend on fixed time and fixed background geometry. When the geometry is rapidly shifting, probability calculations must take those shifts into account. But without a unified theory, the rules for doing so remain incomplete. This uncertainty reinforces why the early universe is considered one of the most important environments for understanding quantum gravity. Researchers often rely on what remains observable today to piece together what happened during this early stage. One of the most useful tools is the cosmic microwave background. This radiation, still present across the universe, carries evidence of the earliest fluctuations. Even though it formed hundreds of thousands of years after the period we're discussing, the patterns it contains reflect the distribution of energy from far earlier times. Another tool comes from observations of the large-scale structure of the universe. By studying the arrangement of galaxies and clusters, researchers can infer how early fluctuations evolved. The early universe also presents questions about the nature of time. In general relativity, time is part of the geometry of spacetime, but in quantum mechanics, time is treated as an external parameter. When these two ideas must work together, the concept of time itself becomes unclear. Without a unified theory, it becomes difficult to determine whether time existed before a certain stage or whether it emerged as spacetime stabilized. This uncertainty doesn't mean time didn't exist. It simply means that our current theories cannot assign it a consistent role in the earliest moments. As the early universe continues expanding and cooling, it enters a stage where energy dominates every part of the environment, but cannot settle into anything that resembles structure. This is a period where the universe contains enormous amounts of energy, yet almost none of it exists in stable configurations. There are no particles with well-defined identities, no long-lasting interactions, and no direction for motion in the classical sense. The universe is full, but full in a way that does not resemble anything familiar. This environment helps bridge the gap between the unstable quantum-dominated stage and the later stages where particles begin forming more reliably. Understanding this environment requires taking a step back from the idea that energy must always belong to something. In everyday life, energy is usually associated with motion, heat, light, or electricity. It belongs to objects or fields that carry it. But during this stage of the early universe, the energy didn't belong to particles because long-lasting particles didn't exist. Instead, energy filled space as fields that fluctuated constantly. These fluctuations were strong enough to prevent the formation of structure, yet they also set the conditions for the first steps toward matter. Energy without form is not a poetic phrase. It describes an environment where the physical systems that normally contain energy had not yet stabilized. The term motion without direction follows naturally once you consider what motion means in a universe where spacetime itself is still settling. Motion requires a background. It requires the ability to track the change in position of an object over time. But here, objects didn't exist in the stable sense, and time intervals short enough to describe motion with precision weren't meaningful. Even when fluctuations acted in ways that resembled movement, they occurred in a setting where the geometry changed too rapidly for consistent paths to form. A fluctuation could shift, but calling it motion in a directional sense would imply a stability in spacetime that did not exist yet. Instead, the universe was filled with activity that did not produce predictable trajectories or lasting patterns. Energy in this environment existed primarily through quantum fields. In modern physics, the idea of a field represents a value that exists everywhere in space, capable of carrying energy even when no particles are present. These fields include the electromagnetic field, the Higgs field, and others that play essential roles in particle physics. In the early universe, these fields were not calm, organized, or in their lowest energy configurations. They were active and constantly changing. When fields fluctuate strongly enough, they can briefly produce particles. But in this early stage, the fluctuations broke down too quickly for those particles to survive. The fields did not produce stable excitations, and the environment was too hot and energetic for particles to persist. The absence of stable particles means the environment was dominated by radiation-like energy rather than matter-like energy. But even calling it radiation can be misleading because radiation today consists of photons travelling through space. Photons have well-defined behaviours, including frequency, direction, and interactions. Here, those behaviours hadn't yet settled into consistent patterns. The energy behaved like radiation in the sense that it filled the universe and influenced expansion, but it lacked the organised wave-like behaviour that photons later display. Instead, the energy was distributed across fields that interacted in highly unstable ways. The expansion of the universe during this stage played an important role in controlling how energy behaved. When space expands, energy density decreases. But at this early time, expansion was not yet dominated by the smoother geometry familiar in later periods. Expansion was happening, but the environment was still small enough that fluctuations in geometry could influence local behaviour. Despite this instability, expansion helped lower the overall energy density gradually. As the average energy density decreased, the fluctuations became less dominant. However, this process was slow enough that energy remained too intense for matter to form. Temperature during this period was extremely high, but describing temperature requires caution. Temperature is a statistical property that requires a distribution of energy among many particles or field modes. While the universe was hot in a general sense because of the high energy density, the environment wasn't yet stable enough to define temperature in the same way it is defined later. Only once interactions become consistent and particles last long enough to exchange energy can temperature become a meaningful parameter. Still, the high energy density ensured that any potential particle that formed was immediately broken apart, contributing to a state where energy lacked the form needed to create structure. Even though the environment lacked structure, it wasn't uniform in every respect. Tiny fluctuations in the fields caused slight variations in energy density across the universe. These variations were incredibly small, but because the universe later expanded dramatically, they would play a role in shaping the large-scale structure of the cosmos. At this moment, however, the fluctuations were part of the overall unstable environment, constantly shifting and interacting with the geometry of space-time. The lack of direction in motion and the absence of stable particles didn't prevent these fluctuations from occurring. They simply prevented the fluctuations from becoming anything long-lasting. The interaction between energy and space-time curvature at this stage is one of the most important reasons the environment lacks stability. In general relativity, energy of any kind contributes to the curvature of space-time. In everyday life, this curvature is incredibly small because the energy densities involved are low. But during the early universe, the energy density was so high that curvature was strong even on tiny scales. Quantum fluctuations in energy caused fluctuations in curvature, and fluctuations in curvature influenced how energy behaved. This feedback loop prevented the emergence of stable structures. Energy couldn't settle in one place long enough to form particles because space-time shifted around it. At the same time, curvature couldn't settle because energy didn't distribute itself predictably. Some theories propose that certain fields during this early stage might have been in states far above their later stable configurations. For example, the Higgs field, which determines the masses of particles today, may have been at a value very different from its current one. This early state could have influenced how particles later gained mass. However, during this stage, none of these field configurations had stabilized. The environment lacked the conditions needed for fields to settle into long-term states. Instead, everything existed in a high-energy environment where even the underlying field values were active rather than fixed. This period highlights the fact that matter requires more than just energy to exist. Matter requires stability. It requires patterns that are preserved over time. It requires consistent rules for interactions. Without stability, energy cannot organize into particles. Without consistent interactions, particles cannot remain intact. Without stable geometry, interactions do not follow predictable paths. The early universe lacked these conditions, and so matter could not appear in a meaningful way. Only when expansion continued enough to reduce the energy density and smooth out space-time did matter begin to emerge. Understanding this stage also sheds light on why matter didn't appear immediately after the initial expansion. The early universe wasn't simply too hot, it was too unstable. High heat can break apart structures, but instability in space-time prevents structures from forming in the first place. Even if particles had been produced consistently, they would not have been able to follow predictable trajectories. Processes like scattering, binding, and decay require a stable background. Without such stability, every interaction dissolves into fluctuations. One of the interesting implications of this period is that motion itself becomes a limited concept. Motion is defined as a change in position over time, but when space-time lacks consistent geometry, positions and time intervals cannot be defined reliably. Even the idea of speed loses clarity. For example, light today moves at a constant speed in vacuum, but during this stage the environment didn't support the concept of a smooth vacuum. Photons, if they existed at all, couldn't travel in straight paths because curvature shifted constantly. Their behaviour was dominated by the environment rather than by propagation. In a sense, motion was present only as the change in fields, not as the movement of particles through space. The lack of direction in motion also reflects the fact that directional distances had not fully stabilised. Motion today can be described with trajectories and vectors, but when geometry constantly shifts, directions lose consistency. A path that seems straight in one moment might bend unpredictably in the next due to space-time fluctuations. The concept of direction becomes unreliable. This is why describing motion at this stage requires focusing on the evolution of fields rather than the movement of particles. Field fluctuations don't rely on consistent geometry in the same way that particle motion does. They simply reflect the underlying quantum behaviour occurring across space-time. Another way to understand this environment is to compare it with the later universe, where energy becomes organised into forms such as photons, particles, and radiation fields that behave predictably. During this early stage, none of those organised forms existed. The energy density was too high and the background too unstable. But this disorganised state wasn't a failure of physics. It was a necessary step in the formation of structure. The universe couldn't begin with particles because the environment needed to stabilise first. Expansion and cooling eventually delivered that stability, but until then, the universe remained dominated by energy without the structures needed to give it form. The transition away from this stage occurs gradually. As expansion proceeds, the fluctuations in geometry become less extreme, distances increase, time intervals become long enough for interactions to persist. Temperatures drop to levels where particles can begin forming and surviving for increasing durations. Even though the universe remains incredibly hot, it becomes organised enough for matter to appear in brief, unstable patterns. Eventually, those patterns become stable enough to allow particles like quarks, gluons, and leptons to exist for meaningful lengths of time. Temperature plays a more defined role as this transition progresses. While the universe remains radiation-dominated, the cooling allows interactions to settle into predictable behaviours. Energy begins distributing across modes that support stable particles. Instead of dissolving immediately, particles survive long enough to interact. The state of energy without form gives way to energy that organises into the first components of matter, but the change does not happen instantly. It requires expansion to reduce the intensity of fluctuations and allow fields to settle. Even during this period of energy without form, the universe was not directionless in its overall behaviour. Expansion provided a general trend that influenced the shape of the environment. However, expansion did not impose direction on local fluctuations. Local interactions were influenced more by quantum behaviour than by the global trend of expansion. Thus, motion within the universe lacked direction, even though the universe as a whole was expanding. This distinction helps prevent confusion between local behaviour and global behaviour, which can look very different depending on the scale considered. By the time the universe moves beyond this stage, it begins allowing particles to form more reliably. These particles still live in an environment dominated by radiation and high temperatures, but they can exist long enough to shape the next stages of cosmic evolution. Interactions begin following consistent rules. Forces begin separating into their familiar identities. Fields begin settling into stable configurations. And space-time geometry becomes smooth enough for general relativity to describe it accurately at larger scales. Reaching the next stage of the early universe means arriving at a moment when energy begins to behave in ways that are more organised, though still far removed from anything that resembles a modern physical environment. This period is often described through the idea of symmetry, but the meaning of symmetry in physics doesn't refer to visual shapes or patterns. It refers to the rules that govern interactions. When a system has symmetry, it means its behaviour remains the same under certain changes. In everyday life, symmetry might mean a face looks the same when reflected in a mirror. In physics, symmetry means the equations describing a system produce the same results when certain transformations are made. During this early stage of the universe, the symmetries governing the fundamental forces were still intact, creating a situation very different from the one we live in now. This idea of an almost universe helps describe what was happening. The environment was not yet the universe as we understand it, because the rules that guide physical behaviour had not split into their familiar forms. Instead, the universe existed in a state where its interactions followed unified principles. This unity wasn't peaceful or simple. It simply reflected the fact that the distinctions between forces we experience today didn't exist yet. The strong nuclear force, the weak nuclear force, and electromagnetism may have been part of a single combined interaction. Gravity was still extremely strong compared to its modern strength, likely participating in a shared high-energy framework where quantum and gravitational rules operated side by side. Understanding these early symmetries requires approaching the idea slowly. In modern physics, each of the four fundamental forces has its own behaviour. Gravity shapes large-scale structures. Electromagnetism governs the behaviour of atoms and light. The strong force holds atomic nuclei together. The weak force controls certain kinds of particle transformations. But in the early universe, before symmetry breaking occurred, these forces were not yet separate. Their differences hadn't emerged. The rules that now distinguished them were not active. Instead, they behaved as different aspects of a unified interaction. When conditions are extremely hot, fields behave in ways that preserve their underlying symmetry. Only when energy levels fall do the symmetries break, causing the forces to differentiate. At this stage, the universe had expanded enough that the most extreme quantum fluctuations no longer dominated. Space-time had become smoother. The energy density had decreased, though it was still far too high for particles to exist in stable forms. But with space-time more stable than before, the fields that describe the universe's fundamental interactions became the central element shaping behaviour. These fields existed everywhere and carried energy even in the absence of particles. Their configurations determined how interactions occurred. Because the symmetries among these fields were still unbroken, the interactions they governed did not behave like the separate forces we recognise today. The idea of symmetry in this context doesn't imply order in a visual sense. It means that if you were able to alter certain aspects of the fields, such as rotating them in a mathematical space, or exchanging components that now represent different forces, the behaviour would remain the same. Today, making those same alterations would disrupt physical laws because the forces have distinct strengths and roles. But in this early period, there was no difference between them. The strength of the interactions, the behaviour of the fields, and the rules governing transformations were identical. This is why physicists call the state symmetric. Despite the underlying unity, this environment wasn't simple. High energies caused fields to behave in ways that didn't allow stable configurations. Even though the symmetries were intact, the fluctuations within the fields remained intense. Particles couldn't form reliably, because the symmetries prevented them from having the distinct properties they would need later. Mass, for example, is determined by interactions with the Higgs field, but during this stage, it's likely the Higgs field had not yet settled into the state that gives particles mass. Without mass, particles behave differently. They don't follow the familiar laws of motion. They travel in ways defined solely by energy and interactions with other fields, not by inertia or resistance. But because none of these behaviors lasted long enough to produce stable particles, energy remained without structure. The early symmetries also meant that certain processes that are forbidden or rare today might have occurred frequently. In modern physics, conservation laws govern how particles interact. But some of these conservation laws arise from broken symmetries. Before the symmetries break, those laws may not have applied in the same way. This doesn't mean the universe was without rules. It means the rules were different because the underlying system was in a different phase. It's similar to how water behaves differently as a liquid than as a solid. Both states follow rules, but the rules differ because the structure differs. In the early universe, the high symmetry phase followed its own consistent principles. Another important aspect of these early symmetries involves the geometry of the universe. When symmetries are intact, the fields that describe space, time, and the fundamental interactions don't differentiate between directions or types of transformations. As a result, the early universe was extremely uniform. This uniformity wasn't a choice. It was a consequence of the laws governing the fields. Because the symmetries didn't allow distinctions between directions or interactions, the universe behaved identically everywhere. This uniformity provided the foundation for the smooth distribution of matter that appears later. Even after symmetry breaking occurs, the early uniformity leaves a lasting imprint on cosmic behavior. However, the uniformity wasn't perfect. Quantum fluctuations still existed. Even within this symmetric environment, small variations in energy density appeared because of the underlying quantum processes. These variations, though tiny, mattered tremendously. As the universe later expanded and cooled, these small differences became the seeds of a large-scale structure. Without them, the universe might have remained perfectly uniform. But the almost universe, the stage where symmetries were still intact, allowed these small differences to emerge and persist long enough to influence later development. This early symmetric environment also influences how particles eventually came into existence. When symmetries break, they produce new rules that govern interactions. These rules give particles distinct properties. They determine which particles can form and how they will behave. For example, once the Higgs field settles into its stable configuration, particles can acquire mass. Before that, the idea of mass doesn't apply. Particles that would later be massive would behave like massless particles. Motion, interactions, and trajectories would be entirely different. But none of these behaviors produce lasting structures because the conditions weren't yet stable enough. The early symmetries prevented the universe from developing complexity too soon. Symmetry breaking can be compared to a change in environmental conditions that forces a system into a different state. Before the change, the system behaves in one consistent way. After the change, new behaviors emerge. In the early universe, this process didn't happen suddenly. It occurred gradually as the universe expanded and cooled. Once temperatures fell below certain thresholds, the fields could no longer maintain their high-energy symmetric configurations. They shifted into new states where interactions behave differently. These shifts mark some of the turning points that eventually allow matter to form. The idea that the early universe had symmetries that later broke has been supported by many lines of theoretical work. Even though we cannot observe the early universe directly, particle physics provides clues. When particles collide at high energies and accelerators, they behave in ways that resemble the conditions of the early universe. At sufficiently high energies, the distinctions between certain interactions disappear. Forces unify temporarily. Symmetry becomes restored in a limited way. This suggests that during the early universe, when energies were far higher, these unified conditions would have been natural. These experiments don't recreate the early universe entirely, but they show that symmetry at high energy is not only possible but expected. Symmetry also governs how fields interact with each other. During this early period, the unified interactions among fields meant that processes occurred that later became impossible. Because the fields had not yet settled into their distinct forms, they could influence each other in ways not allowed today. This cross-interaction may have shaped how fields eventually settled into their stable states. The values of certain constants in modern physics, such as the strengths of the forces or the masses of particles, may have been determined by how these fields behaved during the early symmetric state. One of the most interesting aspects of these early symmetries is how they relate to conservation laws. In modern physics, conservation of energy, momentum, charge, and other quantities are closely tied to symmetries. Removing or altering symmetries can change what quantities are conserved. During the early universe, when symmetries were intact, certain conservation laws may have held in ways that no longer apply. Conversely, today's conservation laws might not have existed yet. Understanding these details helps explain why certain processes happened during the early universe but are forbidden today. Another point that becomes clearer in this stage is why the early universe had to pass through this symmetric phase. The universe couldn't start with forces separated and particles defined. The energy levels were too high for the fields to settle. The symmetric phase was not optional. It was the natural state imposed by the extreme temperature and energy density. Only when expansion lowered those conditions could the symmetries break. This sequence helps explain why the universe has the structure it does today. The stages were not arbitrary. They followed from the physical constraints present during cosmic evolution. The almost universe description reflects that this state precedes the familiar universe, not only in time but in character. The environment behaved according to rules that no longer apply. Once symmetry breaking began, the interactions changed. Distinctions between forces appeared. Particles could acquire mass. Stable forms of matter became possible. But during the early symmetric phase, none of these features existed. Instead, the universe operated under rules that were simple in their uniformity, but prevented complexity from forming. As expansion continued and the symmetries began to weaken, the environment moved toward a state where the first distinct interactions could emerge. The temperature dropped enough that the unified behavior could no longer be sustained. Fields began shifting into new configurations. These shifts, sometimes described as phase transitions, allowed the universe to progress toward the formation of stable particles. Without the early symmetric phase, these later developments would not have been possible. The universe needed to evolve through this stage so that structure could form in a consistent and orderly way. Passing from the stage of early symmetries into the period when the laws of physics begin settling into predictable forms marks one of the most important transitions in the history of the universe. This moment isn't a single instant. It is a gradual shift as the temperature and energy density fall to levels where the unified interactions can no longer remain unified. Slowly, the fields that govern the forces of nature begin taking on their modern configurations. Once they do, the universe starts behaving in a way that supports the formation of stable particles, consistent interactions, and the predictable patterns that eventually allow atoms, stars, and galaxies to appear. Before this shift, the universe wasn't chaotic in the familiar sense, but it was governed by principles that don't apply today. After it, the laws of physics begin to resemble the ones that operate throughout the cosmos now. Reaching this stage requires expansion to reduce the energy density enough for symmetry breaking to occur. Symmetry breaking is the process by which the different forces separate. Earlier, the strong nuclear force, the weak nuclear force, and electromagnetism may have operated as parts of one unified interaction. But as expansion continues, the environment becomes too cool to support the high energy states needed for that unity. The fields that describe these forces settle into distinct configurations, causing differences in behavior to appear. Electromagnetism separates from the weak force. The strong force takes on its characteristic strength. Gravity remains distinct, though still affected by quantum conditions during this period. Each of these shifts establishes rules that govern how the universe evolves. The first time the laws of physics stabilize, even partially, represents the beginning of predictable interactions. Before this point, the environment prevented stable particles from forming. Mass couldn't exist because the Higgs field had not yet reached its modern configuration. Without mass, particles behave differently, and interactions don't follow the patterns we observe today. As the universe cools, the Higgs field finally settles. Once it does, particles begin acquiring mass. This process is sometimes described as particles gaining weight, but it's more accurate to say they gain a property that influences how they move and respond to forces. Mass enables structure because it allows particles to behave consistently over time. When the Higgs field stabilizes, one of the most important transitions in the early universe begins. Before this stabilization, particles either didn't exist or couldn't remain intact. After it, quarks, electrons, and other fundamental particles can form and persist long enough to interact. But this stage still doesn't look like the modern universe. Even though particles can form, the environment remains extremely hot. The temperature is high enough that quarks don't yet assemble into protons or neutrons. Instead, they move within a dense plasma where interactions occur constantly. Still, the fact that particles exist at all marks a major change. The fundamental building blocks of matter are no longer dissolving immediately. They remain present long enough to contribute to later developments. The separation of forces during this period is closely linked to the temperature of the universe. As long as the temperature remains above certain thresholds, the fields associated with each force remain unified. When expansion lowers the temperature, the fields can fall into their lower energy configurations. This is not a matter of the universe deciding how to behave. It's a natural outcome of the energy available. Once temperatures fall below the necessary values, the fields lose access to the high-energy states that preserve the symmetries. They settle into configurations where differences appear. These differences determine how particles interact, how forces behave, and how the universe organizes its contents. With the laws of physics settling down, conservation laws begin taking the familiar forms that govern the universe today. Quantities such as electric charge, baryon number, and lepton number become important in determining how particles interact. Before symmetry breaking, these conservation laws might not have applied in the same way because the symmetries that underlie them were not yet broken. Once the fields settle into stable configurations, these laws become fixed. They determine which interactions are allowed and which are forbidden. These constraints guide the formation of matter and influence the structure of all physical processes that follow. One important aspect of this transition is the appearance of mass differences between particles. Before symmetry breaking, many particles behaved as though they had no mass. Once the Higgs field stabilizes, particles begin acquiring different masses. Some become very heavy, others remain light. These differences shape how particles behave at high temperatures. Heavy particles may remain present for a short time before decaying. Light particles persist for longer periods. These differences influence how energy is distributed and how the early plasma behaves. Even though the universe is still far from forming atoms or stable matter, the distinct properties of particles mark a clear boundary between this stage and earlier ones. During this time, the universe remains a hot plasma of quarks, leptons, and other elementary particles. These particles interact through the newly differentiated forces. The strong nuclear force binds quarks together in brief interactions, though not yet into stable hadrons. The electromagnetic force influences charged particles, guiding interactions in ways that resemble modern behavior. The weak nuclear force governs processes that allow particles to transform into each other. Gravity, though far weaker than the others at this scale, continues shaping the expansion of the universe. These interactions, even though they occur in an extreme environment, follow consistent rules for the first time since the universe began. Another important change that occurs during this stage is the settling of field values across the universe. Earlier, fields fluctuated aggressively. Their values varied rapidly across small distances and short timescales. After symmetry breaking, the fields become more uniform. They still fluctuate, but the fluctuations are smaller and occur around stable values. This stability allows particles to form with well-defined properties. Masses, charges, and interaction strengths no longer shift unpredictably. Instead, they become constants that guide all future behaviour. The settling of the laws of physics at this stage also influences how energy is exchanged. Before symmetry breaking, energy exchanges didn't follow patterns that resemble those found today. Afterward, interactions follow predictable pathways. Particles scatter, transfer energy, and decay according to consistent rules. These processes begin laying the groundwork for later events such as nucleosynthesis, where protons and neutrons eventually form atomic nuclei. Even though nucleosynthesis is still far in the future at this stage, the conditions necessary for it emerge here. Without this stabilization of laws, the later formation of atoms would not occur. This transition also determines how the universe responds to expansion. Once the laws of physics settle, the expansion proceeds in a more predictable manner. The energy density decreases steadily. The behavior of particles becomes increasingly organized. The plasma remains extremely hot, but it becomes easier to describe using well-established principles. Even though the universe is still only microseconds old at this point, the stabilization of laws marks the beginning of behavior that resembles the physical processes seen throughout cosmic history. Another aspect to consider is that the universe becomes more transparent in certain ways as the laws settle. Before symmetry breaking, intense fluctuations prevented radiation from propagating in stable patterns. Afterward, even though the environment remains dense, radiation begins behaving more predictably. Photons still scatter constantly and cannot travel far without interacting, but their interactions follow consistent rules instead of being governed by fluctuating field values. This predictability allows radiation to play a clearer role in shaping the plasma. As expansion continues, collisions among particles become slightly less frequent, not because the temperature drops suddenly, but because the universe becomes larger. The average distance between particles increases. Even though the density remains extremely high, interactions gradually become slower compared to earlier times. This change doesn't reduce the overall activity, but it allows processes involving particle formation and decay to occur in more orderly ways. The environment no longer disrupts each process immediately. Each interaction plays a part in shaping the future composition of the universe. One important consequence of the laws settling is that certain particles begin to fall out of equilibrium. When the universe is extremely hot, particle collisions produce certain particles and destroy them at the same rate. But as the temperature falls, some reactions stop occurring frequently enough to maintain this balance. When that happens, certain particles remain in the universe, even though the environment no longer has enough energy to produce them. This process eventually determines the number of protons, neutrons, electrons, and other particles that persist. But during this stage, the first steps in shifting toward these imbalances begin. This stage also marks the point where symmetry breaking begins influencing the evolution of the Higgs field and other fields that determine particle properties. The stabilization of these fields means the universe can support interactions with predictable outcomes. The later formation of nuclei depends on these outcomes. Without consistent particle masses and interaction strengths, the delicate processes that create atomic nuclei would be impossible. The settling of the laws ensures that the universe can transition from a plasma to a structured environment. Although this stage represents the beginning of stable laws, it still leaves many questions unanswered. For example, researchers continue exploring why certain symmetries break in the way they do. They also examine why particles have the masses they have, and why the strengths of the forces take their particular values. These values influence everything from the stability of atoms to the formation of stars. Understanding why they take their current forms requires knowledge of how fields behaved in this early period. The behaviour during symmetry breaking laid the foundation for all later cosmic structure. Even though this stage occurred in less than a fraction of a second after the beginning of the universe, the consequences extend across all of cosmic history. The predictable interactions that appear here shape the universe's future. They determine how matter behaves, they determine how energy spreads, they determine how structure forms. Without this moment when the laws settled into place, the universe would not have the consistency needed to support stable structures. Stepping into the stage where inflation begins requires taking a slow and careful view of how the early universe changes as its laws settle into consistent behaviour. The foundation for stable interactions has just emerged. Particles can exist for meaningful amounts of time. Fields have shifted into states that allow mass, charge, and interaction strengths to take fixed values. Spacetime has smoothed enough to support predictable geometry. With these changes in place, the environment becomes set for one of the most dramatic transitions in cosmic history. This next phase is known as inflation, a period where the universe expands at a rate far beyond anything observed before or since. The conditions that give rise to inflation develop gradually, but when inflation begins, its effects transform the entire universe in ways that shape everything that follows. The idea of inflation doesn't refer to ordinary expansion, even though the universe was already expanding before inflation begins. Instead, it refers to a sudden and extremely rapid growth driven by the behaviour of a particular field, often called the inflaton field. At this stage of the early universe, the fields that shape physical interactions are settling into lower energy states. Not all parts of the early environment settle at the same pace. Some fields move smoothly into their stable configurations, others take longer, and in some cases a field can linger in a higher energy state briefly before shifting into the state that represents its lowest possible energy. That lingering state is often referred to as a false vacuum, meaning it is not the true stable state, but behaves temporarily as though it is. When a field becomes stuck in a false vacuum, the energy associated with it remains unusually high. In the early universe, this situation had enormous consequences because energy density determines the curvature of space-time. A region with high energy density causes strong curvature, and in cosmology, curvature can lead to rapid expansion. When the inflaton field became trapped in its false vacuum state, the energy density it carried caused space-time to stretch dramatically. This stretching is not driven by pressure or motion in the ordinary sense. Instead, it is driven by the way general relativity relates energy density to expansion. The result is a period where the size of the universe increases exponentially. Understanding why the inflaton field becomes trapped in a false vacuum requires focusing on how fields behave when temperatures are extremely high. At such temperatures, fields may occupy states that are not their true lowest energy configurations. These temporary states emerge because high energy environments allow fields to fluctuate more freely. As the universe cools, the fields attempt to transition to their stable configurations, but depending on the shape of the potential landscape governing the field, a temporary plateau or barrier may exist. When the field becomes stuck in such a plateau, its energy becomes concentrated in the vacuum itself rather than in particles or radiation. This concentrated energy drives inflation. Before inflation begins, the universe is extremely small, still dominated by intense energy density and undergoing normal expansion. But this normal expansion is modest compared to what inflation will produce. At this point, the early plasma remains dense and active. The field values continue shifting. Quantum fluctuations still occur, though less intensely than in earlier stages. The universe has not become calm, but it has become consistent enough that physical laws operate in ways recognizable today. It is within this environment that the inflaton field reaches a threshold, and the conditions become suitable for inflation to begin. The moment inflation takes hold is not a single sharp point. Instead, it represents the time when the inflaton field remains in its false vacuum long enough for exponential expansion to start dominating the behaviour of the universe. Once this expansion begins, the size of the universe increases so quickly that even small regions become vast. Distances that were once microscopic grow to astronomical scales within a tiny fraction of a second. The expansion is so rapid that anything within the universe becomes stretched along with it. This stretching doesn't involve the movement of matter through space. It involves the expansion of space itself. During inflation, the universe expands so quickly that the distances between points increase faster than light itself can travel. This statement doesn't violate relativity because nothing is moving through space faster than light. Instead, space itself expands. Relativity places limits on motion through space, but does not restrict the rate at which space can grow. Inflation uses this fact to create an environment where regions that were once in contact with each other become separated by distances so large they can no longer communicate. This separation helps solve several puzzles in cosmology, such as why different regions of the universe appear nearly identical despite being far apart. The smoothness of the universe today, as seen in the cosmic microwave background, is one consequence of inflation. Before inflation, the universe was small enough that different regions could exchange information. They could share temperatures, energy, and fluctuations. When inflation stretched these regions apart, the uniformity they held became spread across enormous distances. This is why the large-scale structure of the cosmos shows such smoothness, even though the regions involved are separated by distances far greater than light could have travelled since the universe began. Inflation also helps address the flatness problem. In cosmology, flatness refers to the geometry of the universe. A flat universe has just the right amount of energy density to avoid collapsing inward or expanding outward in an uncontrolled way. Without inflation, the early universe would require extremely fine-tuned initial conditions to achieve the level of flatness observed today. Inflation explains this by flattening the universe. When spacetime expands exponentially, any curvature becomes stretched so much that it becomes effectively flat. This doesn't eliminate curvature entirely, but it reduces it to scales that are negligible on observable distances. Another important aspect of inflation is its effect on quantum fluctuations. Even though the universe expands rapidly, quantum fluctuations in the inflaton field continue occurring. Under normal circumstances, these fluctuations would remain microscopic, but inflation stretches them. Fluctuations that began at quantum scales become stretched to cosmic scales. Once inflation ends, these fluctuations remain imprinted in the distribution of energy throughout the universe. They later become the seeds for structure. Regions with slightly more energy density attract more matter. Regions with slightly less attract less. Over time, these small differences grow into galaxies, clusters, and the web-like structure observed across the cosmos. Understanding how quantum fluctuations become stretched requires looking at how inflation changes the behavior of wavelengths. A fluctuation in the inflaton field corresponds to a certain wavelength. As inflation proceeds, wavelengths stretch along with spacetime. Eventually, they grow larger than the distance over which causal interactions can occur. When that happens, the fluctuations become frozen in place. They no longer oscillate or average out. Instead, they remain as small variations in energy density that persist after inflation ends. These variations are incredibly small but essential for the formation of structure in the universe. During inflation, the energy density associated with the inflaton field remains nearly constant. This constancy is unusual because in the modern universe, energy density decreases as the universe expands. Radiation becomes diluted. Matter becomes spread out. Dark energy behaves differently, but it still follows a rule-like pattern. But during inflation, the energy density driving expansion doesn't decrease because it is tied to the false vacuum state. As long as the inflaton field remains in that state, the energy density remains approximately constant. This constancy ensures that the expansion rate remains exponential. Eventually, the inflaton field transitions out of its false vacuum. When this happens, inflation ends. This transition isn't slow. The inflaton field quickly moves into its true lower energy state. As it does, the energy stored in the field becomes released. This release doesn't take the form of calm radiation. It fills the universe with an enormous burst of energy that reheats the environment. This reheat period brings the universe back to temperatures comparable to those that existed before inflation, though the volume of the universe is now vastly larger. Reheating sets the stage for the formation of particles that persist as the universe cools. Even though reheating restores high temperatures, the universe doesn't return to the conditions that existed before inflation. The most important difference is size. The universe is now so large that regions which were once connected are now far apart. The quantum fluctuations that were stretched become the seeds of structure. The uniformity of the early universe has been locked in at enormous scales, and the geometry has been flattened significantly. These changes ensure that the universe proceeds along a path that leads to the cosmic microwave background, the formation of galaxies, and eventually the development of large-scale structures. Another important point about inflation is that it requires the right combination of conditions in the inflaton field. If the field had not been trapped in its false vacuum for long enough, inflation would have been too short to produce the observed structure. If it had remained trapped too long, the universe might have expanded excessively, preventing the formation of matter. The delicate balance between these outcomes depends on the shape of the potential that governs the inflaton field. Researchers continue studying this potential to understand why inflation behaved the way it did. Although inflation may seem like an optional or exotic phase, it helps solve several major problems in cosmology simultaneously. It explains why the universe is nearly flat. It explains why regions of the universe share the same temperature despite being separated by vast distances. It explains why no magnetic monopoles have been detected, even though some theories predict their formation. Inflation dilutes any unwanted relics produced in earlier stages. It also sets the initial conditions needed for the universe to evolve, according to the laws of physics that settled during symmetry breaking. Some models of inflation propose variations in how the inflaton field behaves. Some suggest slow-roll inflation, where the field moves gradually down its potential. Others propose rapid transitions. Despite differences, each model uses the same underlying mechanism, a period of exponential expansion driven by energy trapped in a high-energy field state. The details may differ, but the broad consequences remain similar across models, because the mathematics of exponential expansion is robust. Inflation doesn't last long compared to the full timeline of the universe. Estimates suggest it persisted for a tiny fraction of a second, expanding the universe by many orders of magnitude. Once this phase ends, the universe enters a more familiar thermal evolution. The moments after inflation involve particle production, scattering, and the establishment of thermodynamic equilibrium. These conditions allow the universe to begin forming the earliest particles that will eventually combine into protons, neutrons, and atoms. Even today, inflation remains an area of active research. While the broad framework is widely accepted, the details of how inflation began and how the inflaton field behaved remain uncertain. Observations of the cosmic microwave background provide indirect evidence for inflation through the patterns of fluctuations observed. These patterns match predictions made by inflationary models. Future observations may reveal even more about the details of inflation, including how quickly the inflaton field transitioned out of its false vacuum and what the energy scale of inflation was. By the time inflation ends and the universe becomes filled with high-energy particles and radiation once more, the environment looks very different from the one that existed before inflation began. The size of the universe has grown tremendously. Its geometry is nearly flat. Its fluctuations are imprinted across vast distances, and its energy density has been redistributed through reheating, allowing the familiar thermal history of the universe to begin. With inflation complete, the universe can move toward forming stable matter, and the next stages in cosmic evolution become possible. Moving forward from the period shaped by inflation brings us to a question that naturally appears when thinking about the earlier stages of the universe. Even though modern physics can describe many elements of the universe's evolution after inflation, the period before inflation remains hidden. This isn't because researchers lack interest, or because the tools are inadequate. It is because the laws of physics themselves prevent any information from earlier periods from reaching us. No matter how advanced technology becomes, there are limits built into the structure of the universe that block any view beyond this boundary. Understanding why these limits exist requires looking closely at how the universe expanded, how radiation behaves, and how inflation changed the relationship between regions of space. The boundary being described here isn't a physical barrier in space. It is a limitation imposed by the fact that signals cannot reach across certain distances once the universe expands too quickly. Before inflation, the universe was small enough that different regions could influence each other directly. They could exchange heat, energy, and information. After inflation begins, this ability disappears, because inflation stretches space-time so rapidly, regions that were once connected become separated by distances larger than the maximum distance a signal could travel since the universe began. This maximum distance is called the particle horizon. Anything outside that horizon is beyond the reach of even light. Since no signal can travel faster than light, those regions lose all possibility of communication. During inflation, expansion outpaced the ability of any signal to move across the universe. If two points were separated by a very small distance before inflation, they could interact through radiation or particle collisions. But once inflation starts, the space between those points stretches so quickly that the maximum distance light can travel becomes far smaller than the expanding separation. After that, the 2 points are essentially cut off from each other. The information that existed in one region has no way of reaching the other. Even after inflation ends and the expansion slows, the separation remains too large for signals to catch up. This permanent cutoff means the portion of the universe we observe today includes only a slice of what inflation expanded. Because of this separation, any structure or event that occurred before inflation has no direct link to the conditions we observe now. The effects of inflation wiped out most traces of earlier states. The rapid expansion diluted any relics, smoothed out any irregularities, and stretched quantum fluctuations beyond observable limits. No particles, waves, or signals from earlier times survived inflation in a form that can be detected today. Instead, the only remaining signs of pre-inflationary physics are encoded indirectly in the distribution of energy after inflation, or in the potential shape of the inflaton field. But these signs don't carry information about specific events or conditions before inflation. They only reflect broad characteristics. Another reason we cannot see past the boundary created by inflation involves the behavior of light in the early universe. Light travels at a fixed speed, but that speed is determined through space-time. When space-time expands faster than light can move through it, light becomes unable to bridge increasing distances. During inflation, the expansion rate was so high that light could not cross even tiny fractions of the universe. The result is that the observable universe today contains only regions where light has had enough time to travel since the end of inflation. Anything outside that region remains invisible, not because it lacks structure, but because its signals have simply never reached us and never will. This boundary is sometimes explained through the concept of the cosmic microwave background. The cosmic microwave background is the oldest light that can be observed directly. It formed around 380,000 years after the beginning of the universe, when atoms first became stable and photons could travel without scattering constantly. Before that time, the universe was opaque because photons collided too frequently to travel freely. This opacity prevents us from seeing directly into earlier periods. Even if inflation had not occurred, we still could not observe the earliest universe using electromagnetic radiation, because the earliest light was trapped within the plasma. Only once the plasma cooled enough to allow photons to travel freely did the universe become transparent. Even though the cosmic microwave background limits how far back we can observe using light, inflation adds an additional and much stronger limit. It prevents any signal of any kind, not only light, from reaching us from before the inflationary period. Light was not the only carrier of information affected by inflation. Particles also cannot traverse distances stretched beyond their reach. Gravitational waves also cannot cross boundaries where expansion outpaces their propagation. Inflation creates a horizon beyond which no form of information can pass. The reason this horizon is so restrictive comes from how space-time expansion is woven into general relativity. Expansion isn't motion through space, it is the stretching of space itself. When space stretches, the distances between objects increase, even if those objects do not move. If the stretching happens faster than the speed of light, nothing within those regions can communicate with each other. This is not a violation of relativity because relativity restricts how fast objects can move through space, not how fast space can expand. Because of this distinction, inflation can create distances so large that no particle or signal can ever cover them. From a practical standpoint, this means that any traces of pre-inflationary events are unreachable. No telescope, no detector, and no future technology can overcome the limits created by inflation. The information simply does not exist within our observable region. Even if distant parts of the universe contain evidence of earlier epochs, those parts are beyond our horizon. The boundary created by inflation isn't theoretical. It defines the observable universe. Everything beyond it remains inaccessible. This idea raises a natural question about whether the universe beyond our horizon is similar to the region we observe. Observations of the cosmic microwave background show remarkable uniformity. This uniformity suggests that the universe on large scales appears similar across vast distances. But inflation doesn't guarantee uniformity beyond the observable horizon. It only ensures that the observable region originated from a single small area before inflation. Regions beyond our reach could differ in ways we cannot detect. They might follow the same laws of physics or might not. The inflationary period allows for possibilities that cannot be ruled out or confirmed because no evidence can cross the horizon. Another reason we cannot see past this bound involves the nature of the earliest times themselves. Before inflation, the universe was dominated by quantum fluctuations in space-time. These fluctuations prevented stable structures from forming. Any information that might have existed was constantly disrupted by the environment. Even if inflation hadn't created a horizon, the earliest fluctuations would make clarity impossible. The pre-inflationary universe did not produce clear signals or patterns. Its behavior was too unstable for coherent information to survive. Therefore, even without the inflationary horizon, observing the earliest universe directly would be extraordinarily difficult. The combination of these factors, limited signal propagation, early opacity, quantum fluctuations and inflationary stretching, creates a firm boundary that cannot be crossed. This boundary doesn't prevent us from making theoretical models. It doesn't prevent researchers from exploring possible scenarios before inflation, but it blocks observational verification. No empirical data can reach us because inflation erased the pathways through which it could have travelled. Despite this limitation, some indirect clues may still hint at what happened before inflation. Certain models predict that subtle patterns in the cosmic microwave background might reflect the shape of the inflaton potential or the behaviour of the universe at the very onset of inflation. These patterns wouldn't show detailed events. They would only provide insight into broad characteristics. Detecting such features is extremely challenging. Even if discovered, they wouldn't provide direct information. They would simply help refine theoretical models. Another potential hint lies in gravitational waves. Some models predict that inflation could produce a background of gravitational waves with specific characteristics. These waves might leave tiny imprints in the polarization of the cosmic microwave background. Observations are ongoing to search for these imprints. If found, they could provide indirect support for certain models of the early universe. But even gravitational waves cannot carry information from before inflation. They would reflect conditions during inflation, not earlier. This boundary that hides the earliest universe is not a temporary barrier. It is permanently encoded into the structure of space-time. When inflation stretched the universe faster than signals could travel, it created distances so vast that they remain insurmountable. Even if expansion slowed later, the distances remain too large for signals to catch up. This separation grows over time as the universe continues to expand. Because of accelerated expansion driven by dark energy, distant regions move even farther away. The horizon separating observable and unobservable regions doesn't shrink, it grows. This ongoing separation reinforces the limit. The universe we observe today contains only a fraction of what inflation produced. Everything else remains beyond reach. Even though we can calculate how large the universe may be based on inflationary models, those calculations will always be indirect. They cannot be verified through direct observation because the boundary imposed by inflation cannot be crossed. Understanding these limits helps clarify what cosmology can and cannot achieve. Cosmology can describe the evolution of the universe after inflation with increasing precision. It can examine the cosmic microwave background, large-scale structure, and the distribution of matter. But it cannot access information from before inflation. The earliest phases of the universe remain concealed not because of technological barriers, but because the laws of physics prevent signals from reaching us. This limitation is part of the structure of space-time. As the universe keeps expanding, the observable region remains a finite slice, even though the entire universe may be vastly larger. This slice contains all the information available to science. The boundary around it, shaped by the interplay between light, expansion, and inflation, defines the limits of observation. The earliest stages of the universe remain beyond that boundary, unreachable no matter how far technology evolves. Reaching the point where the limits of observation prevent access to the earliest universe naturally leads to the next question. If the universe hides everything that happened before inflation, how can science attempt to understand what occurred in that unreachable period? Even though no signals can cross the boundary created by inflation, theoretical physics still explores ways to describe what may have happened. These theories do not claim to provide direct images or measurable events from before the observable universe existed. Instead, they attempt to build models that remain consistent with known physics, while extending the framework into regions where the laws of nature become uncertain. This effort doesn't remove the observational boundary, but it provides ways of thinking about what may lie behind it. The earliest universe presents the most extreme conditions known to physics. The energy densities, temperatures, and fluctuations involved were so far beyond anything accessible in experiments that direct testing becomes impossible. As a result, theories that attempt to reach behind the inflationary curtain focus on principles rather than measurements. They aim to remain consistent with what is observed in the modern universe while filling the gaps left by the limits of observation. These theories often rely on mathematical consistency, symmetry principles, and generalizations of existing frameworks. Some introduce new concepts, while others modify familiar ones, but all share the goal of extending understanding into regions where space-time, matter, and energy behave in unfamiliar ways. One of the central theories explored in this context is string theory. String theory proposes that the fundamental building blocks of nature are not point-like particles, but tiny one-dimensional strings. These strings can vibrate in different patterns, and each vibration corresponds to a different particle. In this framework, gravity naturally emerges through one of the vibrational modes. Because string theory includes gravity and quantum mechanics within the same structure, it becomes a candidate for describing the earliest universe. It provides a mathematical setting where the fluctuations of space-time and the uncertainties of quantum mechanics are connected. This makes it appealing for studying conditions where both are equally important. Although string theory remains mathematically complex, one of its contributions to cosmology is offering ways to think about the early universe without requiring space-time to behave smoothly. In string theory, space and time can emerge as large-scale behaviours of deeper structures. At extremely small scales, strings, branes, or other fundamental elements may interact in ways that do not resemble space-time. If this is true, then the earliest universe didn't operate within space-time at all. Instead, space-time formed later, once the fundamental components reached stable configurations. This approach provides a way to think about pre-inflationary conditions without relying on the familiar geometry that breaks down at the Planck scale. Another idea within string theory that relates to the early universe is called the string landscape. This refers to a large set of possible vacuum states that the universe could occupy. Each vacuum state corresponds to different physical constants, particle masses, and interaction strengths. The early universe may have transitioned through different vacuum states before settling into the one that governs our current physics. Although this idea doesn't provide specific details about pre-inflationary events, it suggests that the universe could have experienced conditions different from those observed now. These transitions may have shaped the inflaton potential or influenced how inflation began. Loop quantum gravity is another theoretical framework that attempts to describe the earliest universe. Instead of treating space-time as continuous, loop quantum gravity proposes that space-time is composed of discrete units. These units form networks that produce smooth geometry at large scales but behave differently at the smallest scales. One of the consequences of this framework is that the universe cannot shrink indefinitely. Instead of collapsing into a singularity, the early universe might have reached a minimum size determined by the discrete units of space-time. At this minimum, the universe could undergo a bounce, transitioning from contraction to expansion. This replaces the classical singularity with a quantum transition. The idea of a bounce offers an alternative to the traditional view of the universe, beginning from a single point of infinite density. In the bounce model, the universe existed before the expansion we observe today. It may have undergone a previous phase of contraction. When space-time reached its minimum size, quantum gravitational effects prevented further collapse, causing the universe to transition into expansion. This approach avoids the difficulties associated with singularities and provides a continuous description of cosmic evolution. However, because inflation erases information from earlier times, such a bounce cannot be observed directly. The theory remains a mathematical model that provides a possible explanation for pre-inflationary conditions. Another approach involves the idea of emergent space-time. Instead of treating space and time as fundamental elements, emergent theories propose that space-time arises from more basic components. These components may involve relationships between quantum states, entanglement patterns, or other mathematical structures. In this view, the early universe did not exist in space or time. Instead, space and time appeared once certain conditions were met. This approach changes the way the earliest universe is imagined. Instead of asking what happened before inflation within space-time, emergent theories suggest that before inflation, space-time itself may not have existed. This doesn't mean that nothing existed. It means that the structure we use to define events, locations, and intervals had not yet formed. Once the underlying components achieved the necessary organization, space-time emerged. Inflation may have been one of the processes associated with this emergence. If true, then the lack of observational access to the earliest universe isn't a limitation imposed by distance or expansion alone. It may reflect a deeper fact. The earliest universe did not have the structure needed to produce observable signals. Some theories attempt to connect inflation to quantum processes occurring at earlier times. They propose that inflation might be triggered by fluctuations in fields or transitions between vacuum states. In these models, the pre-inflationary universe could have been in a state of high instability, with rapid fluctuations causing fields to shift until inflation began. While these theories describe possible mechanisms, they don't offer ways to observe the earlier states. The transition into inflation wipes out the details of any prior fluctuations. Another set of ideas considers whether inflation might not have been unique. Some models propose that inflation could occur in different regions of the universe at different times. These models suggest that inflation may produce multiple regions, sometimes called pocket universes, each with its own characteristics. This doesn't mean there are separate universes in a science fiction sense. It means that inflation might produce regions of spacetime that are separated by distances too large for communication. Each region could have different values for physical constants due to differences in how fields settled. Although this idea cannot be observed directly, it provides context for why the observable universe appears as it does. There are also theories that attempt to modify general relativity or quantum mechanics to avoid the breakdowns that occur at extremely small scales. These modifications aim to provide consistent descriptions of spacetime at high energies. For example, some approaches introduce limits on how small distances can be or how energetic fluctuations can become. These limits help prevent infinities from appearing in calculations. While such theories are still being developed, they contribute to the broader effort to understand conditions beyond the inflationary boundary. Another question that arises involves whether inflation itself had a beginning. Some models propose that inflation could be eternal into the future, with different regions undergoing inflation at different rates. But whether inflation extends into the past remains uncertain. Some theories suggest that inflation must have had a beginning. Others propose ways it could have been ongoing, with our observable universe emerging as one outcome of a much larger inflationary process. These ideas remain speculative because they cannot be tested directly. They rely on mathematical arguments rather than observational evidence. The limitations imposed by inflation and the earliest quantum conditions mean that theories attempting to look behind the curtain must rely on the internal consistency. They must agree with everything known about the universe after inflation. They must avoid contradictions with observed data. They must provide mathematical structures that remain stable across different conditions. Beyond that, they remain free to explore many possibilities. This openness allows theoretical physics to investigate a wide range of ideas, but it also means no single theory has emerged as definitive. Despite these limitations, the exploration of the earliest universe remains one of the most active areas of research. Advances in particle physics, cosmology, and mathematical physics continue shaping how theories evolve. New observations of the cosmic microwave background, gravitational waves, and high-energy particle collisions offer indirect constraints on the earliest conditions. These constraints guide the development of theories, helping refine or eliminate models. But none of these observations can provide direct access to pre-inflationary events themselves. The effort to understand what lies behind the inflationary boundary isn't motivated by the expectation of direct confirmation. It is motivated by the desire to build a coherent and complete description of the universe. Even if the earlier stages remain beyond reach, understanding their possible forms helps explain why the universe behaves the way it does now. The structure of the laws of physics, the values of fundamental constants, and the distribution of matter may all reflect choices made or conditions present during the earliest periods. These theories provide ways of thinking about the universe that extend beyond direct observation. They offer frameworks that remain consistent with known physics while exploring the unknown. They cannot remove the boundary set by inflation. They cannot deliver images or data from earlier times, but they can offer possibilities. They can refine understanding. They can suggest new ways of relating the observable universe to deeper principles. Stepping from theories that try to explore the unknowable earlier moments toward a discussion of what the Planck time implies about the nature of time itself requires slowing down again and looking carefully at what it means for the universe to have a minimum scale. The Planck time, defined as roughly 10⁻43 seconds, is not an arbitrary number. It represents the point at which the combination of quantum mechanics and gravity becomes unavoidable. Before this interval, the universe was in conditions so extreme that familiar descriptions break down. After it, the laws of physics begin following patterns that modern theories can describe with increasing reliability. Because of this, the Planck time functions as a boundary, not in a material sense, but in a conceptual sense. It marks the earliest moment where time, as we understand it, becomes meaningful. Understanding this requires looking closely at how time enters the equations of physics. In classical physics, time is treated as a continuous parameter that flows uniformly. Every physical process evolves with respect to time. Particles move, fields change, forces act. The same idea appears in quantum mechanics, where the evolution of a quantum state depends on time as a smooth variable. General relativity also includes time, but treats it as part of the geometry of spacetime. In that framework, time does not flow independently. It is shaped by curvature and interacts with space to form a single four-dimensional structure. Despite these differences, all these theories rely on time being continuous and well-defined. But at the Planck time, this continuity becomes uncertain. Quantum mechanics introduces uncertainty into measurements, and general relativity ties time to the curvature of space-time. When both effects become equally strong, neither theory can provide a consistent description of time. This doesn't mean time ceases to exist. It means that the familiar concept of time, the one that allows processes to evolve smoothly, no longer applies. Events cannot be separated into intervals in the usual way, because the underlying geometry is fluctuating too violently. The moment one tries to measure the passage of time at scales smaller than the Planck time, the uncertainty introduced by quantum mechanics becomes so large that the measurement loses meaning. Because of this, the Planck time represents the earliest moment when time has a physical meaning that fits within existing theories. It isn't that nothing existed before the Planck time, rather it is that the tools of physics cannot describe that earlier interval. The equations stop functioning properly, predictions become inconsistent. Time, as a measurable parameter, cannot be defined. This limitation suggests that time is not an independent background against which events occur. Instead, time is tied to the conditions of space-time. Only once space-time achieves enough stability and structure can time become something that unfolds consistently. Looking at the Planck time also raises questions about whether time is fundamental or emergent. If time cannot be defined before this interval, it may be that time itself arises only once space-time forms a consistent geometry. In this view, time is not a built-in component of the universe. It is something that develops when the underlying structure reaches the necessary conditions. If that is true, then asking what happened before the Planck time might not be a meaningful question. The concept of before requires a sequence of moments, but sequences require time. If time did not exist in a meaningful way earlier, then before no longer applies. This idea does not imply emptiness or lack of existence. It simply means that the tools we use to describe events, position, duration, movement, sequence, depend on time being defined. Before the Planck time, these tools are not appropriate because the system does not support their use. This is similar to how certain physical concepts, like temperature, only become meaningful once a system has enough particles to distribute energy statistically. Before that point, temperature is not defined. In the same way, time may appear only once the structure of spacetime becomes suited for defining intervals. Examining the Planck time also helps clarify the nature of causality at the earlier stages. Causality is the idea that causes led to effects in a consistent sequence. This sequence requires time, but at scales smaller than the Planck time, the geometry of spacetime fluctuates so strongly that the concept of a consistent causal sequence becomes unreliable. Events cannot be ordered clearly. The fluctuation in the geometry introduces uncertainty in how intervals should be interpreted. This doesn't mean causality fails. It means causality cannot be described using familiar rules because the environment does not support those rules. The Planck time also reveals the limits of measurement. To measure a time interval, one needs a physical process that changes in a predictable way. For example, modern clocks use oscillations in atoms or vibrations in crystals. But to measure intervals at the Planck scale, the energy required would become so large that it would distort spacetime itself. Any attempt to probe time at these scales causes gravitational effects strong enough to create inconsistencies in the measurement. This shows that the Planck time is a fundamental limit imposed by the combination of quantum mechanics and gravity, not by technological constraints. Another important idea comes from quantum mechanics, where time is treated differently from space. In quantum mechanics, positions and momenta are operators, meaning they have uncertainty built into them. Time, however, is treated as an external parameter that directs the evolution of quantum states. This difference creates tension when trying to describe the earliest universe, where space and time must both be treated as uncertain. If time acts as an external parameter, it cannot fluctuate. But at the Planck time, the geometry of spacetime fluctuates in ways that affect both spatial and temporal intervals. This conflict suggests that the concept of time in quantum mechanics may be incomplete when applied to extremely small scales. Physicists studying quantum gravity attempt to address this by creating frameworks where time is not treated as an external parameter. Instead, time becomes something that emerges from the relationships among quantum states. In these frameworks, the Planck time marks the point where emergent time begins to behave like ordinary time. Before that, the system does not have the structure needed to support a smooth temporal evolution. This approach helps unify the description of time across different scales, but it remains a subject of active research because it requires rethinking how quantum states evolve. The Planck time also raises questions about whether time is discrete or continuous. In a continuous model, time can be divided into intervals as small as desired, but if the Planck time represents the smallest meaningful interval, then time might be discrete. This doesn't mean time is made of tiny chunks. It means that intervals smaller than the Planck time cannot be defined with physical meaning. Some theories attempt to incorporate discrete time into their frameworks. Others treat the Planck time as a limit on measurement rather than a fundamental unit. Whether time is continuous or discrete remains an open question, but the Planck time plays a central role in motivating the discussion. Another angle to consider is how the Planck time affects our understanding of the origin of the universe. When classical models use general relativity to run the universe backward in time, they reach a singularity where density becomes infinite and time appears to begin. But the Planck time suggests that this singularity is an artifact of using the wrong tools. General relativity cannot describe the earliest universe because quantum effects become too strong. Instead of a singularity, the earliest universe may have been in a different kind of state, where space-time wasn't smooth and time wasn't defined. The Planck time marks the earliest point where classical concepts begin to apply. It does not mark the instant of creation. It marks the boundary beyond which the usual concept of time no longer works. Some theories propose that time extends through the Planck era differently from how it behaves later. In these models, time might have been strongly curved, non-linear, or tied to interactions that do not resemble modern physics. Other theories propose that time might not have existed as a dimension until after the earliest transitions in space-time structure. These ideas don't imply that the universe came from nothing. They suggest that time itself may have been part of the process of the universe forming, rather than a backdrop that existed beforehand. The Planck time also influences how cosmologists think about the continuity of events. In the modern universe, time provides a framework where one event follows another in a predictable sequence. At the Planck time, this sequence becomes uncertain because the fluctuations in space-time affect the definition of intervals. Time does not stop, but its meaning changes. Once the universe expands enough for space-time to stabilize, time becomes continuous in the familiar sense, and sequences become reliable again. This suggests that continuity in time is a property of the universe that emerges only under certain conditions. One more point to consider is how the Planck time affects the interpretation of inflation. Inflation begins after the Planck era, when space-time is already smoothed enough to support consistent expansion. Inflation cannot occur in a state where time is undefined because inflation requires the geometry of space-time to evolve predictably. The fact that inflation occurs means that time must have become meaningful by the point inflation begins. This supports the idea that the Planck time is a boundary between undefined and defined temporal behaviour. Understanding what the Planck time suggests about time itself doesn't provide direct answers about the earliest universe. It doesn't eliminate uncertainty or reveal what happened before inflation, but it clarifies why certain questions cannot be answered using familiar concepts. It explains why the earliest universe cannot be described as a sequence of events in the traditional sense. It shows that time may not be fundamental, but may arise from deeper relationships, and it highlights that the laws of physics are built on assumptions that apply only when space-time has reached the necessary level of stability. Reaching the point where these ideas about time, structure, and limits come together brings the narration into a space where the focus begins to shift from the earliest extremes of physics toward the broader arc of how the universe gradually becomes recognizable. Up until now, the environment being described has been one where the familiar elements of reality exist only as possibilities, waiting for the right conditions. The earliest fluctuations, the formation of space-time, the behaviour of fields, the emergence of mass, the growth driven by inflation, and the gradual settling of laws all represent phases that occur long before the universe becomes the place that forms stars, planets, and life. But even though these phases lie far outside ordinary experience, understanding how they connect allows a clearer view of how the universe transitions from its smallest moment to the long history that follows. Reorienting attention toward the path away from the smallest scales requires looking closely at how each stage lays the groundwork for the next. The Planck era marks the moment when the universe first becomes describable using physical laws. Inflation sets the structure and geometry that the rest of cosmic evolution depends on. The settling of fields shapes the constants and interactions that determine particle behaviour, and the reheating after inflation restores the energy necessary for particle formation. These stages by themselves do not create matter as we know it, but they prepare the environment so that matter can exist. Moving forward from this point involves tracing how the universe shifts from an environment dominated by radiation and fields to one where particles combine, bind, and form increasingly complex arrangements. The first step along this path involves the period immediately after inflation, when the universe becomes filled with energetic particles through reheating. Although inflation spreads the universe to vast scales, reheating restores temperatures so high that the early universe once again becomes a dense plasma. But this plasma behaves differently from the environment before inflation. The laws of physics now follow predictable patterns. The geometry of space-time is smooth. Particles have masses determined by the settled fields. Interactions occur through the four fundamental forces and forms that resemble their modern behaviour. Even though the universe remains extreme by modern standards, it is becoming a place where particles, energy, and fields relate to each other in ways that lead to structure. As the universe continues expanding, the temperature begins to fall, but this cooling is gradual, and the conditions remain hot enough for particle interactions to occur constantly. Among the earliest significant events is the formation of the first stable combinations of quarks. Quarks are bound by the strong nuclear force, but in extremely hot environments the force behaves differently. It becomes too weak to bind quarks into stable pairs or triplets. Only once the temperature falls below a certain threshold can quarks comfortably form protons and neutrons. This threshold is reached within the first microseconds after reheating. When the temperature drops enough, quarks begin forming hadrons, the particles that serve as the building blocks of nuclei. This process marks the first time in the universe's history where persistent particles appear in meaningful numbers. Protons and neutrons do not simply exist momentarily during brief fluctuations. They form in quantities large enough to influence later stages of cosmic evolution. This marks a shift from a universe dominated by energy and fields to one where matter begins to take on recognizable roles. But even here, the environment remains filled with radiation, and particles interact constantly through collisions and scattering. Although hadrons form regularly, they also collide with high-energy photons capable of breaking them apart. Only when the temperature drops further do protons and neutrons remain stable enough to persist without being immediately disrupted. The growing stability of particles opens the door to the next major step, which involves the formation of light nuclei. This period is known as nucleosynthesis. It occurs within the first few minutes after the beginning of the universe's expansion. During nucleosynthesis, protons and neutrons combine through the strong nuclear force to form hydrogen, helium, and small amounts of lithium and deuterium. The ratios produced during nucleosynthesis are determined by the temperature, the density of matter, and the rate of expansion. These conditions remain remarkably uniform across the universe because inflation smoothed out any large-scale differences. As a result, nucleosynthesis produces similar element ratios everywhere. Even though nucleosynthesis represents a major step toward forming matter in recognizable forms, the universe remains dominated by radiation. Photons scatter off charged particles constantly, preventing any light from traveling freely. This scattering keeps the universe opaque. Until electrons and nuclei can combine to form neutral atoms, light cannot pass through the plasma. Because of this, the universe's earliest light remains trapped, carrying information about the conditions of the plasma but unable to travel outward until much later. As expansion continues, the temperature continues to fall. Over thousands of years, the balance between radiation and matter begins to shift. Radiation still dominates the energy content, but matter becomes increasingly important. The expansion also slows because radiation loses influence as wavelengths stretch. Eventually, after hundreds of thousands of years, the universe cools enough for electrons to combine with nuclei. This process, called recombination, causes atoms to form. Once neutral atoms exist in large enough numbers, photons no longer scatter constantly. They begin traveling freely. This moment produces the cosmic microwave background, the earliest light that can be observed directly. The cosmic microwave background represents a distant milestone in cosmic evolution. It preserves the distribution of energy present at the time of recombination. The small differences in temperature across the cosmic microwave background reflect the earlier fluctuations that inflation stretched. These fluctuations serve as the earliest imprints visible in the universe today. They provide evidence for inflation, the uniformity of the early plasma, and the small variations that later grow into galaxies. Even though the cosmic microwave background does not reach back to the Planck era or the inflationary period, it connects the earliest describable stages to the later formation of structure. Once neutral atoms form, the universe transitions into a period known as the Cosmic Dark Ages. During this time, the universe contains atoms, radiation, and dark matter, but no stars or galaxies. The density of matter is not uniform. Slightly denser regions begin attracting more matter under the influence of gravity. Over millions of years, these regions grow denser. Gravity pulls matter inward, causing the first large-scale structures to begin forming. These structures remain invisible for long periods because no light-emitting objects exist. Only when matter compresses enough to form stars does the universe become illuminated again. This progression from the smallest scales to the formation of stars illustrates how the earliest physics influences everything that follows. The Planck time defines the boundaries for meaningful physical descriptions. Inflation sets the structure and smoothness that allow the cosmic microwave background to appear uniform. Symmetry breaking determines the laws and constants that shape particle behavior. Nucleosynthesis sets the initial chemical composition. Recombination allows light to escape, and gravitational growth leads to the formation of stars, galaxies, clusters, and the large-scale structure observed today. Returning attention to the smallest moment again, it's important to recognize that even though direct observation cannot reach that earlier stage, the consequences of that period are visible everywhere. The The smoothness of the cosmic microwave background, the distribution of galaxies, and the behavior of gravitational clustering all reflect the conditions imposed by inflation and the Planck era. The earliest universe cannot be seen directly, but its influence is encoded throughout cosmic history. As the universe grows older, the large-scale structures continue evolving. Galaxies form stars, stars synthesize heavier elements, and those elements become part of planets and life. But all of this complexity rests on the stability established during the earliest moments. If the Planck era had behaved differently, if inflation had not smoothed space-time, or if the fundamental constants settled into different values, the universe might not have formed stable structures at all. Even slight differences in particle masses or force strengths could prevent atoms from forming or stars from igniting. The path from the smallest moment to the present universe is a continuous transformation shaped by physical principles that unfold naturally once the earliest conditions are set. None of the stages occur in isolation. Each depends on the previous one. The universe does not start with recognizable order. It develops order as it expands and cools. The earlier stages may seem disconnected from the modern universe, but they provide the foundation for everything that happens later. Understanding this progression helps place the smallest moment into context. It clarifies that the earliest limits on time and space are not barriers to understanding, but boundaries that shape what can be described. The Planck time represents the earliest moment where time becomes meaningful. Inflation provides the geometry that defines the observable universe. The settling of fields determines the constants that shape matter. Together, these stages allow everything else to follow. This return from the smallest moment isn't a step backward. It's a way of tracing how the universe emerges from conditions where familiar concepts do not apply into a vast cosmos governed by consistent laws. Even though the earlier scales remain hidden, their effects remain visible across the entire span of cosmic history. The universe that begins as a region dominated by uncertain geometry and quantum fluctuations becomes a place filled with stars, galaxies, planets, and the long arc of cosmic evolution.